Good morning. Good morning, everyone. Thank you for being here today. This third webinar we have on 2021 related to International Energy Agency and technology collaboration. We really appreciate all your timing today and the efforts to be here connected from all around the world. Good morning, everyone. Thank you for being here today at our International Energy Agency Technology Collaboration Program activities that we have for today's Saturday, connected all around the world at this section. For the Technology Collaboration Program, we would like to say thank you to all of you at this enhanced oil recovery process we are working this year. Coming together with the different options we have it, we would like to have how we can put together the different technologies we have it from international activities related to enhanced oil recovery processes. We have developed already activities related to microbial EOR, low salinity today, and we will come with more activities for next year. In that sense, we welcome you to participate at this family that we are starting to integrate our EOR TCP with the challenge we have on the environmental conditions today. This comes related to option to put carbon capture storage, energy efficiency, energy storage, hydrogen, emissions, natural solutions, circular economy, renewables, and options that we can put together on this sense. How we can put it, how we can work on that one is something that we really would like to say how our water process, thermal, chemical, gas, come into subsurface mineral, hydrogen storage, ammonia, CO2 storage, subsurface properties, water management and water inclusions is something that we would like to put together. From the International Energy Agency today, we are working with the other technology collaboration programs that around the world had working on this option and activities integrated to carbon intensity processes, energy efficiency projects, renewables, reductions of fugitive emissions and production wells, including CO2 EOR processes. All this is something that we should work on. And we would like to encourage the rest of the participants that we have here today in our scenario that join the International Energy Agency. Please contact us. Today, these are the members that we are working since 2000, putting together the different options and scenarios that we have on these activities. But we welcome more countries that today are working with EOR and how we develop the options to put it. We have representatives in our committee. We have institutions from research institutes, universities, and government delegates that are part of this international family. Today, we are adding volunteers. That's why all this today is happening. You have in contact Sol Reyes, Liz Balbuena, Rosa Cárdenas, and Adriana Castro. And the other, like Georges, like Medi, like Humberto Mendoza, Cristian Patino, as you will see in our next time together on volunteers. All of you are welcome to be volunteers as well here on these scenarios. We are creating a work on the different task force related to the sessions that we are developing today. Sections on study of fluids and interface in porous media, section on surfactants and polymer, on thermal recovery, gas flooding techniques, dynamic reservoir, and emerging technologies. All these come to deliver today a pathway. We are creating a report about how these technologies are going today on EOR. Welcome to participate at this task force. And our actions on EOR is continuous. Today we have higher oil price and our projects, pilots and expansion taking over and fly again back. Welcome to share your knowledge at these options and we have been working. Welcome to be part of the different policies we are working with the governments to generate EOR options and alternatives related to greenhouse emissions, related to CO2 EOR with applications on EOR options and activities and processes with technology and trends. We started last year on December at this way with the webinars. We have been touching 13 countries, different activities scenarios, and we put a roadmap for this year. A roadmap of webinars that closing today. We have been going through the microbial EOR on May with participants all over the world, as you see here. We have as well in situ reactions webinars that come together as well all around the world with the speakers and panelists from different universities and institutions, and an amazing discussion. We would like to welcome you to today, come to the next step, low salinity flooding. And next one is EOR Australia, the annual event. We will invite you. We have already your mail, so we will invite you to the annual event from the different countries of the international agency. On behalf of the executive committee, we would like to say thank you to you and the support to this new journey that we have on the International Energy Agency Technology Collaboration, that we are working with the amazing volunteer committee that today have been contact you and make what we have been happen. Thank you, Medi, Felipe, David, Liz, Sol, Tariq, Medi, Sebastián, Juan Manuel, Jerjes, George Basta, Humberto Mendoza, Julián Caicedo, Cristian, Adriana Castro, Felipe Rojas, that have been working today at the different scenarios we are developed on the policies. We are now outside of what the world is changing today. In our EOR activities, which will include water management, CO2 management, consider greenhouse gas controls and emissions. Hydrogen is as well a great way to put as well in our scenarios together, like part of the solution with EOR. Technology, environment, social, and governance made part of how we can connect it. And that's why we are here today, coming to the low salinity water flooding, putting together how we are going to develop today. We will go from Emirates Arabs, New Norway, United Kingdom, Iran, Colombia, USA, Peru, Brazil, USA, cases that we should study here. Welcome to deliver your questions through the actions, and we will meet you into the panel on live with the panelists. Thank you to the panelists, Dr. Emma Al-Salabi, Dr. Tina Punterbo, Dr. Pedran Mansari, Dr. Ivan Darío Piñeres, Dr. Hassan Mahani, Dr. Eduardo Manrique, Dr. Geoffrey Finnick, Master Joseph Sinchitulo, Dr. Hami Rahima, Dr. Lucas Gomez, Dr. Dandina Rao. With that, we would like to welcome you today and all the best on this journey today. Thank you.
Good morning, ladies and gentlemen. It's my great pleasure to be with you in this virtual webinar that is organized by Technology Collaboration Program of Enhanced Oil Recovery by International Energy Agency on low salinity water flooding. This is Dr. Imad Ash-Shalabi is speaking to you. I'm an assistant professor in the Petroleum Engineering Department at Khalifa University of Science and Technology in Abu Dhabi, United Arab Emirates. So today I'm going to share with you some of my expertise about low salinity water injection as a potential standalone to hybrid EOR technique. Starting with the outline of this presentation, first I will be talking about motivations and objectives of this presentation. Then I'll be talking about some of the lab applications of this EOR technology in sandstones and carbonates. After that, I'll be talking about the controlling mechanisms for incremental oil recovery by this low salinity water injection technique. After that, we will go through some of the field applications of this technology in sandstones as well as carbonates. Afterwards, we will be talking about the hybrid applications of this technique. And at the end, I'll wrap up this presentation with some key takeaways. So starting with the motivations and objectives, well, we know that every reservoir go through 3 recovery stages. First, the primary recovery, which is mainly on depleting the natural energy of this reservoir. Then after that, we go through the secondary recovery, which is more or less based on pressure maintenance of the reservoir. And after that, we move to tertiary recovery methods, or what we call by enhanced oil recovery methods. So talking about water flooding as a technique, it has been used for years by field operators for pressure maintenance purposes, as well as for pushing the oil towards the producer wells. However, lately, field operators as well as researchers started paying attention to the chemistry of this injected water. And by that, I mean the total dissolved solids in their TDS, as well as the ionic composition of that water, because this is expected to cause some oil, brine, and rock interactions, and this will be translated into additional oil recovery. And this is, ladies and gentlemen, what we term as low salinity or engineered water injection, which is under the others category of the tertiary recovery or in enhanced oil recovery methods. So let me talk about the difference between these two terms, low salinity or engineered water injection. Starting by low salinity water injection, we usually refer to this by diluting of the injected water. So we keep the amount of solute constants in here and we add more of the solvent. And this results in a total reduction in the total dissolved solids. Here is a schematic of the problem. Imagine that you have 8 particles of solute in 100 milliliter of a solvent. Then all what we do, we increase the solvent in there to about 200 milliliter, and that will change the concentration from 8% to 4%. So this is an example of dilution by low salinity water injection. Now, on the other hand, if I talk about engineered water injection, then here basically we refer to modifying the ionic composition of this injected water, and that's through hardening or softening of some key potential ions in the water. The engineered term basically is used to denote that proper screening is needed for coming up with what you can call your favorite recipe, cocktail of ions that will maximize the effect of rock and oil and brine interactions, and it will result in incremental oil. So this needs more screening compared to just diluting the water using low salinity water injection. Talking about the objective of this presentation, first we will highlight the potential of low salinity water injection technique. Then we'll discuss the importance of choosing the right water recipe, or what I call cocktail of ions. And then we will emphasize on the synergistic effect when combining this low salinity water injection technique with other enhanced or recovery techniques. Talking about the lab applications of this low salinity water injection in sandstones and carbonates. Starting with sandstones, the technology was first introduced by Bernard in the 1960s, where he injected low salinity water to some of the cores that contains clay, and he witnessed the swelling of the clay. From that time, several researchers have done several extensive laboratory works, starting with Tang and Morrow in 1997 and afterwards. Al-Adasani and others in 2012 reported the positive impact of low salinity water injection in the secondary mode through 214 core floods, as well as in the tertiary mode through 188 core floods. And researchers basically observed that there should be an important factors controlling these mechanisms, like the clay presence is of importance, as well as the water salinity has to be within a certain range, usually between 1,000 and 5,000 ppm. I need to highlight that so far, most of the works that's been done in sandstones, they're mainly based on low salinity water injection or water dilution. Talking about carbonates on the other side, the start of trying this technology in carbonates was a bit delayed, and that's due to the effect I just mentioned, that they related this technology to the presence of a clay. And as carbonates, they have a minor clay composition to no clay, then researchers thought it will not have an effect. However, several researchers documented that the presence of some of the key ions, which we call them potentially determining ions, including mainly sulfate, calcium, and magnesium, will control low salinity effect in carbonates. Other researchers like Gupta and others in 2011, they said, well, it's not all about these three ions. Other ions will be important, like borate or even phosphate, or even if you just soften the water by removing the hardness of those calcium and magnesium ion, that will cause you more incremental oil. Some other researchers, they even witnessed a certain optimum concentration of that sulfate in order to maximize the effect of incremental oil recovery by this technology. However, here I need to stress on that we need to be careful with the use of sulfate ions, because that usually will cause scale formations and potential reservoir souring in our reservoirs. So I need to highlight that mainly the effects in carbonates were concentrated on engineered water injection, which is by ion manipulation through softening or spiking of some of those ions. However, low salinity water injection by dilution also was tried in carbonates, and here I'm just referring to a study that was done by Yusuf and others in 2011 in Saudi Aramco, where they basically injected seawater and they got a certain oil recovery. Here's like 70%. And then every time they were diluting the injected seawater, they were getting more incremental oil. For example, twice diluted, it will result in 7%, 10 times diluted, 9%, 20 times diluted, 1.6%, and then 100 times diluted, it reached to a plateau. So they documented an incremental oil recovery of about 18% out of using this technology in their core in lab scale. And that's mainly through low salinity water injection and through dilution. Talking about the controlling mechanisms for this incremental oil recovery by this technology. And here I'm summarizing one of those figures shared by Rotondi and others in 2014, where we see that the evolution in those mechanisms with time. So authors, they were referring to fine migration as a process, alkaline flooding, which is similar to what is happening with surfactant injection, multi-ion exchange, salting in effect, mineral dissolution, pH induced wettability change, and water microdispersion. In general, there is no still clear idea about what is happening and what is controlling the incremental oil recovery. But most of the researchers more or less agree on wettability alteration as one of those main controlling phenomena. Here in sandstones, if we talk about the mechanisms, I'll stress on multi-ion exchange mechanism, which is controlling wettability alteration. So in sandstones, we have clays that they're negatively charged, and we have the oil with its carboxylated groups that is negatively charged. And usually we have a positively charged ions that they're working as a bridge between these two negatively charged groups. So what is happening with the injection of low salinity water injection, we're basically breaking those bridges, and that will cause a release of the oil and more incremental oil. However, if we need to talk about the wettability alteration mechanism in sandstones, then there should be several factors that they lead to this incremental oil. Presence of a clay is important. Oil composition, and especially having that total acid number, becomes important. Formation water should be rich in divalent ions, magnesium and calcium. And low salinity water injection level, as what I said previously, it should be between 1,000 to 5,000 ppm. Also, the initial reservoir wettability plays a role. Usually, the greatest effects were pronounced for oil wet or mixed wet reservoirs. And lastly, high SOR saturation in the reservoir after high salinity water flooding needs to be there. Well, this in order to have more pronounced effect of the technology, as well as justify the economics of the project. Talking about the mechanisms for carbonate, well, again, wettability alteration is there. However, here, as what I said before, we believe that there should be some key ions that cause this wettability alteration, and I'm referring here to sulfate, calcium, and magnesium. The higher the concentration of those at higher temperatures, the more pronounced the effect. And usually most of the researchers also agree on the multi-ion exchange mechanism, but this happens differently than those in sandstones. So here I'm referring to one of those mechanisms. So basically, we believe that carbonate reservoirs at reservoir conditions, they're usually positively charged, or they have positively charged sites. And then the negatively charged oil carboxylated group will be sticking to that. Now, thanks to having sulfate in the water, which has a great affinity to the carbonate rock surface, as it has a negatively charged, then it will get close to the positively charged carbonate surface, and that will stimulate a repulsion between the sulfate and the negatively charged carboxylated group. Then thanks for the presence of calcium and magnesium, which they will form complexes with that carboxylated group, and they will release it to the surface, which results in more incremental oil. Talking about some of the field applications in sandstones and carbonates, here I'm showing a summary where several pilots of low salinity water injection have been applied to different parts of the world. So we can see some of them there here in the Middle East, in Russia, in North and West Africa. We can see some in Europe, and also in the North American continent. And I need here to stress on that most of those projects were mainly targeting sandstone reservoirs. However, we have some recent pilots in carbonates, and here I'm just highlighting two of them. Here I'm referring to the study made by Lager and others in 2007. Well, they looked into 18 of those field scale pilots, and they reported the incremental oil. And you can see on an average where we have about 14 to 15 percent of incremental oil recovery using this technology. As a study case, I took the case in the Endicott field in Alaska, where they were started basically with the 3 single well chemical tracer tests. And here I'm summarizing some of their observations for those 3 tests. So we can see that for the 3 tests, whenever they inject the high salinity water, then they dropped it to low salinity water, in this case about 1500 ppm. Then they see a reduction, a pronounced reduction in residual oil saturation. So for the first test, that was about 9 saturation units of reduction, and the second one about 11, and the third one about 17. So that was a great incentive for them to go ahead and implement the first interwell application, where they used 1 injector and 1 producer that they're about 1,000 feet apart. So what they have done, as you can see here in the graph, seawater has been there for a while, and then as soon as they started their low salinity water injection, then 3 months later, you see the effect on oil rate. So oil rate was a certain level, then as a result of injecting low salinity, it has increased. And they reported an incremental original oil in place in about 12%. Then they started basically looking into what could be the reason that is controlling the incremental oil, and is there a relation between these different tests, the ones that they have done at their core in the lab, and the 3 single well chemical tracer tests, as well as the interwell test. So what they have done, they have correlated the incremental amount of oil with the clay content that is there in each one of those experiments, whether they're in the lab or field scale experiments. And what we can see here clearly is with increasing the clay content in the rock, then you can see a higher incremental oil recovery. So the incremental oil recovery has something to do with the clay content. And later they even confirmed that by measuring some effluent iron concentration at the field level. And this iron is expected it has been produced basically by the ion exchange reactions that is happening at the surface of the clay. So that basically kind of supported their observation. We should not forget the first full field commercial application of low salinity water injection that is currently taking place in the Clare Ridge field in UK, and it started in 2017. So basically, they have reported so far a 7% incremental oil compared to conventional water flooding at a cost of just $3 per barrel for the development, which is really encouraging for the application of this technique, especially if you have already water flooding surface facilities there in place, then there is not much that you can add in order to have your low salinity effect. Talking about the carbonates, as I said earlier, there are just very few pilots, but there are way more coming in the pipeline. So here I'm reporting one of the first application in carbonates, which was done in Saudi Arabia, and that was in the form of 2 single well chemical tracer tests. So what they have done, basically, they have injected a high salinity water followed by a low salinity water, about 10 times dilution, and they reported about 7% reduction in residual oil saturation to conventional water flooding, which is basically a pronounced effect, and it shows that low salinity effect is there. And I need to highlight that here what they have applied is just as what you can see here, dilution of the water. The question is that are there any other applications or hybrid applications of low salinity water injection? And the answer is yes. And that's basically a good news for field operators that they do not believe in the sole effect of low salinity water injection by itself. Then combining this technology with other EOR techniques, then it will bring positive aspect on your enhanced oil recovery. Here, I'm showing some of those hybrid applications of low salinity that has been proven at the lab scale. First, low salinity water injection and polymer flooding. So basically, once you reduce the salinity of the water, then you need less chemicals, less polymer to meet your target viscosity. And that really reflects positive in your CAPEX and OPEX requirement, as well as you have a better microscopic and volumetric sweep efficiencies. Another application, which is the hybrid low salinity water injection with surfactant flooding. With low salinity, usually some of those released oil blobs might be retrapped again because capillary pressure is still active. But thanks for the use of surfactant, which basically kills that capillary pressure, and it will help in producing more of the oil. Also, we should not forget the positive effect of low salinity in reducing surfactant retention. A third application for the hybrid effect is low salinity water injection along with gas or CO2 injection, where reducing the salinity of the injected water will cause more CO2 gas to be dissolved in the oil. And it has been reported that in this case, low salinity will boost oil recovery rate, while CO2, especially if it's miscible, that will control mainly the reduction in residual oil saturation. And there are several applications that they are in progress now in the lab, but I just decided to share some of the main ones in here. Also, for the field applications, I need to highlight that low salinity water injection and polymer has been applied at the field scale, and that's in the Greater Bergen Sandstone field, which is in Kuwait. And here I'm showing basically the production of this field with time, and we're up to 2010. Once the water cut started increasing, then they decided to apply low salinity water injection. And the way they have done it basically as a series of 3 single well chemical tracer tests. One with the seawater or formation water, and then one with low salinity water, and the third one which a combined or hybrid low salinity water and polymer injection. And they reported basically 7% reduction in conventional residual oil due to this hybrid technique. Some of the main key takeaways at the end of this talk, I want to highlight that low salinity water injection has a high potential as a standalone, as well as a hybrid enhanced oil recovery technique. Also, I need to say that wettability alteration is believed to be the main reason for incremental oil recovery by this technology. A very important thing to stress on is that the improvement in oil recovery using this technology is really a case dependent, and you need to make sure you understand those factors before you have any pronounced effect. And those factors are the temperature, the pressure, the rock mineralogy and initial wettability state, the oil composition, and most importantly, the water composition. I hope you enjoyed this talk, and I look forward to your questions. Thank you and stay safe.
Our next presenter is Dr. Tina Puntervold. She's an associate professor at the Department of Energy Resources at the University of Stavanger in Norway. And she's also currently an assistant director of the National IOR Center of Norway. Until recently, she served as an associate editor of Elsevier's Journal of Petroleum Science and Engineering. Dr. Tina Puntervold has a master in physical chemistry and a PhD in petroleum engineering. Before joining the academia, she worked as a field engineer for Schlumberger. Dr. Tina Puntervold will present to us, is there a low salinity EOR potential on the Norwegian continental shelf? And she will tell us about some experimental core fluiding and spontaneous inhibition studies on outcrop sandstones, where low salinity water injection has shown very promising oil recovery results compared to injecting formation water or seawater. Stay with us and remember to send all your comments and questions on the chat. They are going to be discussed later on the panel section. And thank you so much, Dr. Tina Puntervold, for being with us today.
Hi, my name is Tina Puntervold, and today I will be presenting Is there a smart water EUR potential on the Norwegian continental shelf? In 2018, the Norwegian Petroleum Directorate, together with Imperial College, studied 27 of the largest oil fields on the Norwegian continental shelf, investigating technical EUR potential from employing different IOR methods. They found that the technical potential was about 600 million standard cubic feet oil equivalents, and at $60 per barrel, it amounts to approximately 1,500 billion NOK. They also found that the most promising IOR methods on the Norwegian continental shelf was hydrocarbon miscible WAG, smart water polymer, CO2 miscible WAG, and low salinity and surfactant polymer. In 2020, Imperial College, together with Norwegian Petroleum Directorate, performed a new study on the overall EUR potential on the Norwegian continental shelf, looking at incremental oil volumes. And it was calculated based on including only the single top process per field, and this time they included 46 fields. They performed advanced screening, including operational, economic, environmental considerations, and the likelihood for implementation. And from the technical screening only, incremental oil was about 700 million standard cubic meter, by including the operational and economic costs, the technical potential decreased to 344 million standard cubic meter, and now the technical potential was highest with hydrocarbon miscible gas WAG, low salinity polymer, low salinity only, and CO2 miscible WAG. When they also included environmental considerations into the screening, the technical potential decreased even more to 282 million standard cubic meter. And now we can see that the most promising methods were hydrocarbon miscible gas WAG, low salinity polymer, and CO2 miscible WAG. But we see now that the low salinity only has significantly increased. At the Clare Ridge field at the UK sector, they are employing low salinity water injection from day one, and they expect to recover 40 million additional barrels from this field. So if the UK can do it, why not Norway? So what is smart water or low salinity water? Well, smart water is injection brine with modified ionic composition, and the composition is dependent on reservoir mineralogy. Low salinity water is an injection brine which has low salt content, but both these methods aim to improve wettability and reservoir sweep. And in both methods, no expensive chemicals are added, so they are environmentally friendly. And how does the smart water work? It improves sweep efficiency. It works both in carbonates and sandstones, but the mechanism for the wettability alteration is different. So if we look here in the figure, and if you inject the formation water or any other type of brine, then it will displace the oil from this larger pores. But while if you inject the smart water that can alter wettability, you can also make the water invade the smaller pores and displace the oil from the smaller pores. To observe wet EUR by wettability alteration, we need a reservoir that is not completely water wet. Otherwise, there is no smart water EUR potential. So we need to understand the initial wettability of the reservoir. And initial reservoir wettability is dictated by the reservoir chemistry and interactions between the crude oil containing polar organic acids and bases, the brine, especially the formation water salinity and the composition, and the rock. And the rock can be carbonate rock minerals or sandstone rock minerals. And these provide mineral surface reactions with the water and oil. And in most chemical processes, temperature is important. Regarding rock chemistry, the reservoir rock is normally divided into carbonate and sandstone, and the carbonate may contain chalk or limestone, both are calcium carbonates, or dolomite, also including magnesium. There could also be other minerals present like anhydrite, calcium sulfate. Sandstones contain, it's not just a sandstone, they contain quartz, clays, feldspars, and other minerals. And the clays could be present as kaolinite, elite chloride at different in different amounts. Feldspars could be sodium feldspar, calcium feldspar, or potassium feldspar, present in different amounts. And other minerals could be, for instance, anhydrite, calcium sulfate, or carbonate as a cement. But carbonates are normally positively charged at slightly alkaline conditions, and sandstones are normally negatively charged at slightly acidic conditions. But of course there are exceptions. But there's generally large variation in reservoir rock mineralogy. And there's different chemistry involved in initial wettability generation and wettability alteration processes. Brine chemistry. To observe any EOR effects, we need an injection water that is different from the formation water, because we need to disturb the chemical equilibrium between the crude oil, the brine, and the rock established in the reservoir. So we must be able to unstick the oil from the rock surface. And how can we do that? Well, one solution is to inject the smart water. Crude oil is not a homogeneous phase. It contains polar organic acids and bases that have affinity to the rock surface, and these influence the rock wettability. And they are also crude oil anchor molecules at the surface. And the organic bases could be represented by this small molecule quinoline, and carboxylic acids could be represented by this small molecule benzoic acid. And the charges of these molecules are depending on pH. So at low pH, the base is positively charged, but at higher pH, it loses its charge and becomes neutral. The acids at low pH is neutral and protonated, while at a higher pH, it loses the proton and becomes negatively charged. And this has, of course, effect on their affinity for the rock surface. To evaluate the efficiency of any water-based EOR methods relying on wettability alteration, we need to understand the initial wettability of the reservoir. Sandstone mineralogy is composed of quartz, clays, feldspars, and cementing material. And the clay surface is very large, and it contains negative charges due to the cation exchange capacity and deficiency in the mineral lattice. And these negative charges need to be charge balanced by either inorganic ions from the brine phase or by components and ions from the oil phase. So the initial wettability is then a competition between the ions present in the brine phase and the oil components. In addition to understanding the initial wettability, we also need to understand the wettability alteration mechanism for being able to create better reservoir simulation models. And we're not going into all the details. We have proposed chemical wettability alteration methods that tries to explain the low salinity smart water EOR effect. And basically, when you inject a low salinity brine, there is a local increase in pH observed, and that increase in pH can then transform the basic and acidic material from a charge that has affinity to the surface to a charge that has not affinity to the surface. And by this charge change, the oil components can be released from the surface. So is there a smart water ERA potential? Here we have a reservoir A at Norwegian continental shelf at high temperature above 130 degrees C. We have tested different brines and looked at oil recovery using these brines and how efficient the brines are in displacing the oil. So the first brine we tested was a low salinity brine. We also tested the formation water. We have tested a modified seawater, and it's modified to contain less divalent ions compared to a standard seawater. And what we can see from the oil recovery test is that if you inject the formation water, you reach an oil recovery level up to this point here. If you instead inject a low salinity brine, oil recovery dramatically increases and reaching a higher oil recovery plateau. If you inject the seawater, standard seawater, it displaces oil to this level and it's quite a slow process. But if you inject a modified seawater, it's a much faster process, but ultimate oil recovery level is the same as in a standard seawater process. So from these results, we can say that we get 40 to 50% additional oil produced by low salinity water injection, and seawater does not seem to be the best injection brine. And remember that these most reservoirs on Norwegian continental shelf, they are offshore fields. And the reason for seawater not being as efficient is the amount of divalent ions present in the seawater that prevents the wettability alteration and especially the pH increase. What we also could observe is that the low salinity water injection delays the water breakthrough and producing a lot more oil after just the one pore volume injected. We have another reservoir B at the Norwegian continental shelf, also at high temperature, where we have also tested low salinity effect after seawater flooding. So we have injected the formation water. We have injected the low salinity brine, which produces much more oil than the formation water. And we have also injected seawater, which again produces the least amount of oil. And if we switch from seawater injection to low salinity injection, which could be a reasonable scenario offshore, then there is no extra oil recovered by low salinity injection. And the same thing we see here. In this case, we switch from formation water to seawater to low sal, but there's hardly any extra oil recovered. So low salinity injection is most promising, providing high oil recovery within a reasonable short time. And also, this is very important that there is no low salinity ER effect observed after seawater flooding in this case. A third reservoir C at Norwegian continental shelf, high temperature. We have only two cores here, but we have tested low salinity water injection versus seawater water injection in these cores. And to be able to secure or to be sure about our results, we have switched directions. So in this left case here, we did first a seawater flood, and then we restored the core and did a low salinity flood, and the low salinity flood produced more oil. And in the other core, we did the opposite. So in this case, we did first the low salinity flood, and then after restoration, the seawater flood. And by doing this, we could minimize any core restoration effects on the results. So in both cases, we see that low salinity injection recovers more oil, more than seawater in both cores. And so it is valid results. And the reason for this small difference in this case is that this field is not really the best candidate. So what's next? Hybrid EOR potential. So for outcrop core, we did the core flood, where we first injected smart water, which is a low salinity brine and sandstone, and then we switched to injecting a low salinity with polymer. And we saw an ultimate recovery with low salinity polymer of 86% of the oil in place, which is a lot. And the reason for this high oil recovery is that during the low salinity water injection, we see we alter wettability by the smart water, and then that creates more residual mobile oil after the low salinity water injection, because there's redistribution and less and oil entrapment. And this oil is efficiently displaced with HPAM polymer. So is there a smart water EOR potential on the Norwegian continental shelf? Yes, the answer is yes. Laboratory work indicate potentially large EOR potential, especially if the smart water or low salinity brine is injected from day one. We see accelerated oil production and also lower water production with time. So this could be positive for the lower total CO2 emissions. So it's important to know about the mineralogy. Then to study the initial wettability is important. We need to know about the reactivity of the ions in the injected brine, and then we can design the best brine for that reservoir to improve the oil production. The authors acknowledge all oil and energy companies that have funded research work over the years, and we also acknowledge Research Council of Norway and the industry partners of the National IOR Center for support. Thank you very much, and I will be glad to answer questions. Thank you.
Thank you, all the assistants today, and welcome. Please to do the registration. We have today all these amazing countries coming here at this event. Thank you, Dr. Halik. Thank you, Dr. And we have different institutions connected today as well, that we would like to encourage you as well to please register and put the questions for our great speakers that we have today. Thank you, Dr. Tina. Thank you very much.
Our next presenter is Dr. Pedram Masari. He is a research associate of reactive flow in porous media in air science at the University College of London. He has bachelor, master, and PhD degree in petroleum reservoir engineering, and he has been the lead researcher of experimental and modeling studies in EOR and reactive multiphase flow through porous media. Dr. Pedram has also worked with the Science Clean Energy Consortium for advanced characterization of shale oil and gas reservoir and reactive flow modeling for geothermal reservoir in Iceland. And his research interests are EOR in shale oil and gas, characterization of reactive flow in underground reservoirs, and multiphase flow for EOR scenarios. In his presentation, Screening Suitable Crude Oils for Low Salinity Water Injection, Dr. Pedram will tell us how characterizing fluid interactions through microdispersions can screen crude oils for low salinity water injection. Thank you very much, Dr. Pedram, for being with us today, and thank you very much for your presentation.
Hello, everyone. My name is Pedram Mahzari. I'm a research associate at University College London, and today in a few slides I'm trying to show a mechanism called microdispersion formation as a capability to screen suitable crude oils for low salinity water injection. So in this talk, you'll see the results from sandstone reservoirs, carbonate reservoirs, basically a series of laboratory experiments at core scale and fluid-fluid interaction tests to validate our understanding about the role of microdispersion formation and fluid-fluid interaction for efficient low salinity water injection. The outline of my presentation is we will have a very brief introduction about water injection in oil reservoirs and enhanced oil recovery. Then I'll briefly overview the rock and brine and oil brine interactions. Then I'll show the summary of the results of the series of core scale experiments on sandstone and carbonate formations. And then after that, we will have our conclusion. As a background and introduction, low salinity water injection has been in the industry for more than 3 decades, and there's a consensus that the wettability alteration is the main cause behind the additional oil recovery, and it leads to detaching oil from the surface. However, what is debatable is the mechanism behind the wettability alteration, and it is a very crucial factor in determining whether the low salinity water injection is going to work. So the cornerstone of the low salinity effect is wettability alteration and hence oil polarity. And the oil polarity can be determined by asphaltene and resin content and acid-base components. So as this illustration shows, the oil can cut through the water film and adhere on rock surface directly. So if low salinity wants to change the wettability, it should detach this oil which is connected, which is adhered on the rock surface. And what we think, and in the next couple of slides, we will see the evidence for that, that the dominant fluid-fluid interaction happening between oil and brine can change the oil polar characteristics. So in this slide, you can see that from the right, there is a micromodel image showing that when we inject low salinity water, these bright ones are water, low salinity water, interacting with the oil. There are some dark spots forming within the oil. Then this on the middle image, you can see that this very brownish phase formed between the oil and the low salinity water. This is called microdispersion, which is the dominant fluid-fluid interaction process happening between low salinity water and crude oils. And we have taken samples from this brownish phase, and we have analyzed it through ESEM, through FTIR, infrared analysis, and also Carl-Fisher titration, and we identified that this is a packet of water surrounded by oil polar components in a very nanoscale sizes. So in the next few slides, you'll see the body of evidence that we are presenting to show the impact, the dominant impact of fluid-fluid interactions in sandstone and carbonate rocks. What we basically did is we used the same rock, but various crude oils. And if our results were convincing, this would show that there is a chance that if we have the crude oil, if we can identify these microdispersion and oil polar components, and we are able to screen the the positive crude oils for low salinity water injection. So here we have, firstly, we are showing the sandstone results, and they are taken from this paper published in 2019 SP Journal. So for our methodology, we have used same reservoir, sandstone reservoir rock. This is an ESEM image of the rock showing that we have clay, and the clay content of the rock is average of 5% for the cores. And this is a 4 sample cores that we have. We are showing their properties. You can see that they have 20% of porosity, around 100 millidarcy of permeability, and the initial water saturation that we have established was around 10%. So for the fluids we use in this set of experiments, we use 16 different crude oils, and this is a list of the original crude oils that we have used. And in order to make the more crude oils, we have blended crude oils, and we have also pre-contacted crude oil with low salinity, and we remove the micro dispersions, and they call treated crude oil. And also we use the original oil unadulterated crude oils. And also we have also used, we mixed the crude oil, blended crude oil with the negative ones and the positive one, i.e. negative one is the crude oil without microdispersion, positive one is a crude oil with plenty of microdispersions. And for the brine one, we kept it same for all experiments. The high salinity brine is 100 kppm, and for low salinity brine is 500 ppm, and it has monovalent and divalent. For all experiments, we have first desaturated the core with high salinity water, then we injected, we established initial water saturation, then we aged the core for 3 weeks under pressure and temperature. Then firstly, we displaced the crude oil with high salinity water, which is called secondary water flood, to reach the residual oil saturation. And then we switched to low salinity water injection to recover the remaining oil, as it called tertiary water injection, tertiary low salinity water injection. And this is the temperature and pressure under which we performed the experiment. So here we're showing just the results of the tertiary low salinity water injection for those interested in secondary water flood and the spontaneous imbibition experiment that we perform on these cores. They can be referred to the paper published in SP Journal for these set of experiments. So this is the results of the 16 crude oil. We performed the tertiary low salinity water injection on same sandstone rock. And at the first glance, what you can see is different crude oil would lead to different response to low salinity water injection. It means it actually, this is the crucial factor in determining the impact, the results of the low salinity water injection. The other thing is, we in our system, we saw that the maximum oil recovery that we can obtain in laboratory scale can be as much as 10%. The other factor that I want to mention is that if we have checked the repeatability, we have checked that one, and this blue one and this brown one, they are the same crude oil tested on the same rock, and you can see that it's almost on top of each other, showing that our results are repeatable. The other factor that I want to highlight here is that for tertiary low salinity water injection, even in the lab scale, what we saw is it takes around 1 pore volume, let's say less than 1 pore volume, to see the first oil produced by low salinity water injection. So in our experimental approach, what we did, which was a bit novel, that we tried to mix the crude oil to come up with a new blend of the important or negative crude oil with the positive crude oil. We mix it with 50-50 to reach to another new crude oil. If we have important crude oil, which were negative low salinity water injection, and with very rich crude oil, which resulted in a very high additional oil recovery. And if we get something in between these two, it shows that the content of the polar component, the polar content of the crude oil is actually the determining factor for low salinity water injection. So here there is the results of the tertiary low salinity water injection using 4 different crude oils. This one is the weak crude oil, important or negative crude oil in terms of the microdispersion formation. And this brown one is the very rich crude oil performing very well in terms of low salinity water injection, and we blend them. One is called mix 2, one is called mix 3. The mix 1 and mix 2 and mix 3 are the ratio of the mixture between the important and the rich one. And you can see that by varying the ratio of the blend, you get different results in terms of low salinity water injection. And actually the result is in between these two important and rich crude oil that we have used, showing that the microdispersion characteristic of the crude oil is actually the main mechanism behind additional oil recovery, and it can be a really useful tool to screen the crude oil before doing any core flood, before doing any studies in terms of the additional oil recovery by low salinity water injection. So here is very interesting piece of experimental results we can see. So here again we have a potent or rich crude oil with a very high efficiency to tertiary low salinity. Then we have another one which is called an asphaltic crude oil. This is a DP crude oil. It has performed fairly good to low salinity water injection, but we have 2 more crude oils we have. One is blended of this asphaltic crude oil and the potent one. And you can see that adding good components of the rich crude oil to the asphaltic crude oil has boosted its performance, and we have more additional oil recovery. But another one is that we have taken this rich crude oil, we have pre-contacted with the low salinity, and then we carefully remove that brownish phase, which we call it microdispersions. And you can see that its performance actually reduced remarkably. You can see that from more than 10%, the additional oil recovery dropped to less than 2%. This would indicate that that brownish phase, that interfacial fluid interaction, which we call it microdispersion, that's actually that is the main and predominant mechanism behind additional oil recovery. And actually this singular slide shows that if we want to screen the crude oil and if we want to identify the positive crude oil, we need to just identify and characterize its potency to form microdispersions. So here in this slide, what I have done is I summarize the results of ultimate additional oil recovery by low salinity water injection versus microdispersion ratio. So this microdispersion ratio is what it is formed after contacting with low salinity water injection divided by this initial bond water of the crude oil before any experiments. So you can see that there is a clear monotonic relationship between IOR by low salinity water injection and microdispersion ratio of that crude oil using same rock. So if we have a very low microdispersion ratio, there is a very little additional oil recovery. And if we have very high potency of that crude oil towards in terms of microdispersion formation, we will get very high additional oil recovery by low salinity water injection. So that this simple curve can show that there is a very direct relationship between the oil polar component responsible for microdispersion formation and additional oil recovery by low salinity water injection. So what about Carbonate formation. If the predominant mechanism is a fluid-fluid interaction processes, so it should work in carbonate formation as well. So in the next few slides, you'll see the results of the same approach, same methodology applied for carbonate formation. For that, there is a paper published, and I encourage you to go through the paper to see the details of how we perform the experiments and how we get the results and analyze the results. For the experiments performed on carbonate rocks, we use different crude oils, but we kept the rock and the brine same. We analyzed 8 crude samples, and you can see we have the microdispersion ratio plotted versus the crude oil number. And we have this crude oil, which is a good crude oil, a very rich and potent crude oil responding to microdispersion formation, very good. And then we have other crude oils, relatively negative ones. We selected these number 3 and number 2, and we tested on the carbonate rock to see how it performs. So in terms of the methodology, same one as sandstone one. We used 3 cores taken from a carbonate formation from Middle East. 3 crude oils were used. 1 positive one, as you saw from previous slide, 1 negative one, and 1 which is we used the positive one, and we removed the pre-contacted crude oil and low salinity, and then we removed the interfacial phase to remove the microdispersion, and we perform for the core flood experiments, we perform secondary high salinity and tertiary low salinity water injection. Again, here I'm showing just the results of the tertiary low salinity. For the sake of time, you can go through the paper and see the results of the secondary water flood. So here we are showing the oil recovery versus pore volume injected for tertiary low salinity. The red one, the solid red one, is for positive crude oil. The green one is for impotent or negative crude oil. And the other red one is, and you see the very flat red one. This is a positive one, but we treated crude oil and removed the microdispersion. You can see a very sharp impact of removing microdispersion from the crude oil. When we remove the microdispersion from this red one, it's actually become a very negative crude oil with no response whatsoever to low salinity water injection. So in addition to the oil recovery, we have tested other hypotheses like pH changes for carbonate. You can see again, the pH is going up for all 3 cores or all 3 experiments similarly, which indicates that the pH variation is not a responsible cause behind the additional oil recovery by low salinity water injection. In terms of the ionic interaction between the aqueous solution and the rock, here I have plotted a calcium to sodium ratio is divalent divided by monovalent ratio. You can see that all the 3 cores, they have similar changes. They going up and then coming up, coming down. Same trends in terms of the sulfate to chloride that we have plotted here, because the low salinity water is a dilution of the high salinity. The ratio in the injection water is the same for both brines, although the total salinities are different. But you can see that again, in terms of the sulfate, we don't have a conclusive results for the relationship between the ionic changing of the water and additional oil recovery. Hence, the only thing that is controlling the performance of the low salinity water is the polarity or the potency of the crude oil towards formation of the microdispersion. So to explain how this microdispersion can lead to additional oil recovery and a detaching of the oil from the rock, we have this illustration here. We think that when the oil is changing wettability initially and these polar components are adhere to the rock, when the microdispersion is forming the low salinity water, then we will having a dislocation of the polar components because they are surrounding the packet of the water, which we call it microdispersion, and then it weakens the bond between the oil and the rock, and hence we have dislodging of the crude oil from the surface, which would lead to additional oil recovery. And therefore, there should be a balance of the forces, which leads to a mobilization of the oil. So how we can quantify microdispersion characteristic of the crude oil? The test should be performed in a spontaneous manner because the microdispersion, as we identify from macro model and visualization experiment, they form spontaneously. We should not have any mixing or agitation, because mixing and agitation will trigger the conventional emulsions. But this microdispersion, they form spontaneously. Any quantification and characterization should be carried out under temperature, because temperature would contribute and facilitate actually the formation of the microdispersions. One thing that we have observed is the microdispersion will not break by centrifuging the fluids. So if they form, they are unbreakable unless chemically something is added to the system. In order to quantify the amount of microdispersion, Kyle-Fisher titration can be used to measure water content, because the main characteristic of microdispersion is this nano water molecules dispersed in the crude oil. Still, the wettability state of the system is very important. If we have a very strong wettability, either water wet or oil wet, in our experiments, we didn't see significant additional oil recovery irrespective of microdispersion formation. So as a conclusion or synopsis of our talk today, so we have seen that in sandstone and also in carbonate, fluid interactions can be studied for screening the crude oils. Also, we have seen the water film beneath the wetting crude oil may not be active, as active as it was believed, because if it was active, then water, the double layer expansion, ion exchange, the other important processes can be in play, but we saw that the predominant mechanism is basically microdispersion formation. The very solid thing that we identified is if the oil cannot form microdispersion, we would expect negligible additional oil recovery by low salinity. If the oil is very potent towards microdispersion formation, still we need to identify the favorable wettability state of the rock in order to achieve the additional oil recovery by low salinity water injection. Thanks for your attention. I would like to thank my supervisors, my collaborators, and students helping me delivering the results and this slides and the talk. Thank you.
Good morning. The next speaker is the Dr. Ivan Piñeres Torrijo, Master Degree in Chemical Engineer from the University of Barcelona, and PhD from University of Stamford. He is now working as a postdoctoral research in reservoir chemistry at the University of Stamford. His main research topics are reservoir chemistry, SCEL, a study with the high focus on winnability and smart water EUR process in both carbonate and sandstone reservoir. Dr. Piñeres has participated in the fundamental research to improve the chemical understanding from reservoir when the well-believed and well-believed alteration process. He has allowed contribute in the industry project sponsored by international oil companies with the objective to evaluate the EUR potential from a specific oil reservoir. Welcome, Dr. Piñeres Torrijos. Thank you for your being here today.
Hello, my name is Iván Dario Piñeres Torrijos. I'm researcher in reservoir chemistry at the University of Stavanger and the National IR Center of Norway. I'm very glad of participating in this virtual meeting and panel in low salinity water flooding. I'm here today to present the work Overcoming Challenges and Hurdles for Smart Water EOR Characterization. This is a summary of lessons learned for improved smart water EOR characterization. So let's get started. And I want to begin my presentation with this phrase. The most dangerous phrase in the English language is, "We have always done it this way." For me, this is a very powerful phrase that represents the challenges that we had faced when we had tried to understand smart water EOR processes, because the smart water EOR processes have challenged our way of thinking in relation to initial wettability, core restoration protocols, fluid flow in porous media, and EOR effects. So at the University of Stavanger, we prefer the term smart water, which was coined by our main mentor, Tor Ostad, who founded the Smart Water EOR group. We use the term smart water because it covers an umbrella of processes that is dependent on the mineralogy. The smart water process in carbonates is different from the smart water processes in sandstones, and these terms covers both of them. However, other companies have different terms to refer to a similar process. BP calls it low salt, and low salt is a trademark. Shell also uses a trademark, which is designed water. Exxon uses advanced ion management, and Saudi Aramco, Total, and Repsol have joined our proposal to call these processes smart water. Other researchers also use the term ion-tuned water. But what can this smart water do for us? Here I have two examples in sandstones and carbonates. The example of the left is a sandstone's viscous flood, and we can see that with formation water we can obtain approximately 40%. However, when we inject on smart water, we disrupt the chemical equilibrium and we can obtain a 10% more of crude oil. In addition to this, we observed an increment in the pH. This points out to a disruption in the chemical equilibrium of the system. At the right-hand side, you can observe a process of spontaneous imbibition followed by a viscous flood with formation water. They're signalized in green. Then, a smart water is injected and we obtain a significant increment in oil production. In this case, the smart water is seawater. Seawater at salinities of around 33,000 ppm is a smart water for carbonate systems. But what do we see in common here? We observe a significant increase in oil recovery by changing the injection brine composition. We also observed that the EOR effect is highly dependent on the natural chemistry of these reservoir systems. And this effect is caused by an increased sweep efficiency that is due to increased capillary forces and a change towards a more water-wet state. I also want to debunk the myth of low salinity. Here I have an example where we have a smart water EOR effect at higher salinities. In this example, we have a formation water of 25,000 ppm composed of calcium chloride, and a smart water of 40,000 ppm, which has a higher salinity than the formation water. And we observed an EOR effect. However, this response is a bit delayed due to slow calcium desorption, but the effect is there. And we can tell that the water composition is more important than the salinity. And this low salinity definition also comes from a process of optimization in the composition of the smart water brines. Here I have more evidence. We have two parallel systems. We have used the same core material here, and we observe the effect at 25,000 ppm in a tertiary mode. We observe an increment of approximately 10% in the recoverable oil after reaching the plateau with the formation water. So we're convinced that the composition is more important than the salinity. So a salinity focus will perhaps create challenges in understanding these processes. We have to be open-minded and capture the entire complexity of these systems. And one thing that it's very important when understanding these processes is that the mineralogy is very important because they control the chemical path of these reactions. In carbonates, we know that the surface charge is positive, while on sandstones is negative. We also know that some trace minerals like calcium sulfate could play an important role in smart water processes. However, calcium sulfate could represent a negative effect due to the presence of divalent ions if a dissolution occurs. There are other minerals that can also influence the pH in sandstones. And on the other hand, in carbonates, we have buffered pHs due to dissolution of carbonates, while on sandstones we have an acidic nature. And this pH could influence the affinity of the polar components that creates, one, the initial wetting, and second, the wettability alteration processes. So we have different smart water compositions depending on the lithology. In carbonates, we know that the potential determining ions are calcium, sulfate, and in a lower degree, magnesium. However, in sandstones, the monovalent ions can induce an equilibrium rupture. Typical smart water compositions in carbonates could be seawater, modified seawaters, and in some cases low salinities if there is anhydrides present. And in sandstones, we can have compositions with low concentrations of divalents that can differ from the formation water composition to induce a shock. And we also have typically low salinity brines. So it happens that low salinity brines are smart water in sandstones, but we should not focus only on the salinity. In smart water processes, a high potential occurs when we have mixed wet systems and high oil saturations. A reduced potential is found in systems where the systems are already water wet and the high water saturation is present. This is due to the fact that smart water is a process of wettability alteration. So if the system is already too water wet, there is not much room to play. Here I have an example about another myth, which is low salinity in carbonates. At the bottom line, you can observe the effect of formation water. This is a formation water of 65,000 ppm. And then at the top, we have 3 examples of smart water. And as you can see, the recoveries go above 50%. Among them, we have seawater and some modified seawaters. However, if we take seawater, which contains potential determining ions, and we dilute that, and we adjust it to a salinity of 1,600 ppm, which is a low salinity brine, the effect of oil recovery drops. So this diluted seawater had no significant effect in chalk. In this case, this chalk is a very pure carbonate mineral and has no anhydride, so we don't have a source of potential determining ions. Another example is a published work by Youssef et al. From Saudi Aramco, where they showed low salinity effects in carbonates. They used here limestone material, and we can observe that with seawater, they obtained approximately 70%, and as they were diluting this brine, they observed incremental oil recovery. This was due not precisely to the fact of a low salinity in itself, but we know that several limestone cores contain anhydride. However, this is not explained in this work. But at the University of Stavanger, we have a work with a similar material, and we found out that these trace minerals that carry calcium sulfate minerals can contribute to the smart water EOR effect in a positive way. And this is done by dissolution once that a low salinity brine is injected. Here you can observe that effect after the 3rd stage, where the low salinity is injected. This dissolvable anhydride is usually not seen by XRDs, but is detected in the effluents of the brines. Another important aspect of this type of processes is the co-restoration practices. We need reliable co-restoration procedures in order to first determine correctly the initial wettability of the systems, and secondly, to estimate properly the wettability alteration effect. However, this is not an easy task. We have, for instance, an example where these trace minerals in carbonates were affecting the initial wettability of these systems. This is a core restoration, and one of these cores was preflooded with the distilled water. Both of them are outcrops, and the other one was not clean. And what we observed is that the non-clean core behaved very water wet, while the clean core had a reduction in the water wetness. So these minerals can affect the wettability by increasing the water wetness if they're present from before. Another aspect in core restoration is the effect of crude oil. Crude oil can influence the wettability by the presence of polar organic components. These polar organic components can be measured by the acid and base number. And we also know that they are dependent on the pH of the systems. In sandstone systems, the pH is normally acidic, and in carbonates, the system is alkaline. And these states will influence the affinity of these polar components towards the surfaces. We also know that in relation to this type of components, the basic material will absorb more in sandstones than the acids, while we have the opposite situation in carbonates. The acids will influence more the wetting than the bases. So we have done some experiments where we have measured the effect of crude oil exposure in core restorations. And we had observed that in different systems, that if we float for a longer period with larger volumes of crude oil, the cores, we will affect the wettability of the cores. So the cores that are exposed to more crude oil will have a lower degree of water wetness in both spontaneous imbibition, as it is shown in this figure, and in viscous float processes. Here we have two different systems, and we observe the same trends. So we observe increased oil exposure that reduces the water wetness of these core systems. We had also observed the more water wet the core is, a higher ultimate recovery is reached during forced imbibition. So in this case, we have a spontaneous imbibition, and when the core is set in a viscous float, we obtain higher recoveries than with the core that was floated with a larger amount. This works for both of these examples. These results are not in line with the work done by Jadhun Anand and Morrow in 1995, where they say that the maximum recovery is reached at mixed wet conditions. So we have validated this, and we keep exploring this trend, but we think that we need to re-evaluate the fundamentals on wettability understanding. So in the process of evaluation, we mentioned that the wettability is a very important aspect. And we try to compile several lessons to try to control more this process of wettability. We have changed our methods of cleaning. So we have used we incorporated into our protocols mild cleaning solvents with kerosene and heptane instead of toluene and methanol, which is our classical solvents. And it is because they can retain more polar components on the surface. However, when we're restoring and we're injecting oil, this wettability is also affected. Here we can observe the effect in a second restoration. When we inject 5 pore volumes of crude oil in a second restoration, we can observe how the wettability changes from one restoration to another. So in this way, we wanted to summarize our lessons, and we have learned that the mild cleaning preserves quite a lot of the polar components on the surface and retains wettability, which is important to be closer to the evaluation of reservoir wettability in some cores, especially in reservoir cores. We also understood that the amount of crude oil is important, and that to obtain reliable and constant measurements of fluid saturation is very important. So we had used the desiccator technique during the initial water saturation. And we had set a strategy for wettability reproduction to improve our procedures using the mild cleaning solvent, which is a new alternative. and using the desiccator technique and minimizing the amount of crude oil. And through this, we obtained the reproduction of wettability in carbonates. Now we had also obtained the reproduction of wettability in a second restoration in relation to the first restoration in our laboratory. This has helped us to improve the quality of the smart water UR effects evaluation. We also have developed a lot of screening techniques depending on the mineralogy, and that helps us to speed up the process of evaluation on smart water. And as an example, we have also shown how a process of a low salinity can be evaluated under this type of screenings and can show when the conditions are set for a good deployment of smart water, or when we can have a more challenging situation, as it is this example, it is not refill, where the conditions were too water wet. Well, with this, I want to close this presentation. I want to thank the University of Stavanger and the partners of the National IR Center. Here are the acknowledgements, and thank you very much for your attention.
Thank you all that you are connected here today. Please go ahead and answer the questions and as well get feedback as well into the chat. Thank you very much. Let's continue on this great journey today with our low salinity water flooding. Thank you for all the experience and thank you for everyone.
Our next presenter is Dr. Hassan Mahani. He is a professor of petroleum engineering at Sharif University of Technology. He has over 16 years of industrial and academic experience. He has worked for about 12 years at Shell Technology Centers in the Netherlands as principal investigator, research scientist, and SCAL expert. His research is geared toward fundamental understanding, quantitative evaluation, modeling, and prediction of multi-phase flow in porous media with application to IOR and EOR, geoengineering, and environment. He has authored or co-authored more than 60 technical papers published in scientific journals and conference proceedings. Dr. Mahani is an active member of SPE, Interpol Society, and Society of Core Analysts, SCA, and currently serves as Associate Editor for SPE Reservoir Evaluation and Engineering and Journal of Petroleum Science and Engineering. He holds a PhD degree in petroleum engineering from Imperial College London and master's degree in chemical engineering from Sharif University of Technology. Dr. Hassan Mahani will present to us time scales in low salinity water flooding, Iran. Remember to leave your comments and questions on the chat. They are going to be discussed on the panel section. Thank you, Dr. Hassan Mahani, for being here with us today.
Hello and welcome to my presentation. Before I start my talk, I would like to thank the organizers for inviting me to this meeting. In this presentation, I'm going to talk about the timescales involving low salinity water flooding and how they would impact the way we evaluate low salinity water flooding. Low salinity water flooding is an enhanced water flood. In recent years, research activity on this method has sharply increased. This technique improves the microscopic sweep efficiency and can accelerate oil production, lowers the water cut, and delays the breakthrough time of the injection fluid. It can be applied in secondary mode and in tertiary mode, but the earlier it is applied, the higher would be its efficiency. Low salinity water flooding changes the crude oil brine rock interactions and shifts the thermodynamic equilibrium. Response to low salinity water flooding is determined by various co-Br interactions at the solid-liquid and liquid-liquid interfaces as shown in this ternary diagram. The type and magnitude of co-Br interactions lead to different mechanisms which would affect the wettability state of the system and the pore scale events. Multiple length scales are involved in low salinity water flooding, from atomistic or molecular scale, where we believe the initial interactions start to occur, to pore scale, pore network scale, Darcy scale, and field scale. There is 10 to the 9 to 10 to the 12 order of magnitude change in length scale observed in this process. To observe oil recovery by low salinity water flooding, or LSR, at the continuum scale or Darcy scale, the low salinity effect, or LSE, at lower scales should be transmitted to upper scales, something that does not always happen. In other words, not any low salinity effect can lead to low salinity recovery, and that may explain lack of response in some systems. Low salinity water flooding is a multi-timescale process. There are fast and slow sub-processes at the solid-liquid and liquid-liquid interfaces, which may occur simultaneously. The slow sub-processes, such as film phenomena and diffusion, can take hours to days to complete, whereas the faster sub-processes have a time scale of milliseconds to minutes. The time effect, which is the focus of this talk, should be accounted for in the design of experiments to properly evaluate low salinity water flooding for the candidates. The first observation which demonstrated the time effect came from droplet scale experiments on clay-coated substrate. These tests showed that wettability alteration, which is one of the main effects of low salinity water flooding, is a very slow process. The experiments show that upon exposure of droplets to low salinity flooding after equilibration with high salinity, wettability change is not instantaneous and can take several days before we see full detachment of oil from the substrate. In some cases, we did not see detachment and just saw a contact angle change. Systematic investigation using various brine salinities and dilution show that the time scale is really large and does not depend much on the dilution factor. The time scale of wettability change was much larger than that predicted by the Fickian diffusion in the film, and also the time scale of dynamic IFT change. A similar sets of experiments were conducted for model carbonate surfaces to probe the rock type dependency of the time effect. Use formation water, seawater, diluted seawater, and modified seawater with different PDIs and nanoparticles. As you can see in this contact angle diagram, after switching brine from high salinity to low salinity or modified seawater, we do see a wettability change towards a more water wetting states with all of the brines. However, again, this wettability alteration is very slow, and it can take several days to complete. Contact angle tests were performed ex situ or outside porous medium. To investigate low salinity effect in a porous medium and verify the time effect, we can conduct microfluidic experiments using a Cayley functionalized macromodel to mimic sandstones and to check how the contact angle changes in situ upon exposure of system to low salinity and whether we observe any low salinity recovery. Here we see the micromodel results after flooding an all-saturated model with high salinity. High salinity has recovered the easy oil in the center of the pores and has left behind some trapped oil in the corners of pores. Based on the curvature of the menisci in individual pores, we see that this is an oil-wet system in the presence of high salinity. Upon exposure of the system to low salinity, we do not see any immediate effect. Therefore, we shut in the system and allowed the system to age with low salinity or the soaking time. After some time, we do see a change of contact angle in individual pores towards a more water wetting state, and we do see later on pushing of the oil out of the pores via the film flow and formation of some de-wetting patterns. Later on, we do see coalescence of the oil ganglia and production of this oil from the system. But nevertheless, this is again a very slow oil recovery process. We repeated the micromodel experiments with a calcite micromodel fabricated using isolated spar calcite crystal. The experimental procedure is as before. We flooded an all-saturated model with high salinity first. High salinity, as you can see, has recovered the easy oil in the center of the pores and throats and has left behind some oil films and some trapped oil in the corner of the pores. Whereas on the menisci curvature, this represents a strongly oil-wet system in the presence of high salinity. After low salinity flooding, we do not see any visible change up until 5 days. Thereafter, we see formation of some de-wetting patterns in the corners of the pores, and it is accelerated over time, leading to gradual recovery of oil from the pores and from the film area. The pore after 16 days, as you can see, is almost clean, and the wettability has changed to a more water wetting states. Now let's look at some other results showing the time effect. Upon low salinity water injection into a porous medium, it starts mixing with the in situ high salinity water while displacing it. Replacement of high salinity with low salinity is necessary to observe any low salinity effect. However, it is a slow process, particularly in dead end pores, because it can only occur via a water film. In these slides, we see the results as a function of oil polarity. This slide is for a non-polar oil such as hexane. Blue represents the in situ high salinity water, gray represents the hexane as a trapped phase, and pink represents the injection low salinity water. In this slide, we see the time-lapse imaging showing that it takes about 23 minutes to replace the trapped high salinity in the corner of the pores with low salinity water. In this slide, we see results when 2% oleic acid was added to the nonpolar oil to increase its polarity or acidity. Here, we look at the results for a pore doublet, but we have checked other pore systems and the results are more or less the same. Here we note that the replacement time of high salinity water trapped in the pore doublet, shown here, increases to 3.5 hours just because of increased oil polarity. This is a similar test, but with 10% oleic acid added to the nonpolar oil. Again, we look at trapped high salinity water in a pore doublet. As you can see here, we note that by increasing the acidic component in the oil, the mixing time or the replacement time has increased even further to 4.2 hours. We also tested a crude oil sample which has natural acidic components as reflected in its acid number. We use different pore system, a heterogeneous pore system and a pore doublet system, which results in different types of trapped high salinity water. Nevertheless, we note that the mixing time is not much dependent on the type of the pore system, and it's about 6 hours, which is even larger than that observed for synthetic oils. To understand this further, we note that the crude oil has a stronger oil polarity as reflected in its more negative cytopotential. We believe that the increased oil polarity should have slowed down the transport of ions via the thin water film, as we will see later on in the following slides. Our hypothesis is that electrodiffusion in charged thin film controls the timescale, because Fickian transport model cannot explain the observed timescale in both wettability alteration and mixing experiments. The reason for the slowdown is that the ionic transport occurs in a charged thin film. Both oil and rock surfaces are charged and they induce an electric field in the film, which has a strong effect on the ion mobility, apart from the concentration gradient that exists. We have modeled the thin film phenomena via CFD simulations. The non-Fickian transport was modeled by coupling Poisson-Boltzmann equation with Nernst-Planck equation. The Nernst-Planck equation is the extended form of Fickian diffusion, which has diffusion term and electrokinetics term. The argumented Navier-Stokes equation was used to simulate hydrodynamics and the evolution of disjoining pressure in the film. The computational domain and grid are shown here for an oil droplet sitting on a substrate. The governing equations were solved for ionic transport via water film bound by oil and substrate. The film shown here is first equilibrated with high salinity, then exposed to low salinity on the external boundaries. Now let's look at some results. CFD simulation shows that the charges on oil and rock surfaces slow down the diffusion of counterions due to the competing action of concentration gradient and electrical potential gradient. Therefore, cations are retained in the film while anions are repelled from the film. We have calculated the effective diffusion coefficient in the film for anions and cations, represented here by the EF. The results show a significant reduction of effective diffusion of cations by a factor of 10 to 20 compared with Fickian diffusion. This is in agreement with the experimental results. We found that the electrical behavior of oil and solid surfaces have the predominant effect on the effective diffusion, while salinity gradient imposed in the system and local variation in film thickness and length have a secondary effect on the timescale. It's important to note that in this simulation, we did not account for surface reactions and multi-ion exchange processes in the film. We are going to account for this in our future simulations. In this slide, we try to simulate the effect of oil polarity on the ionic diffusion as previously seen in the mixing experiments. We compare 4 different cases where the surface charge of the oil is increased while the surface charge on the solid surface remains fixed. In all of the cases, the thin film is first equilibrated with high salinity, then exposed to low salinity from this point. And then we look at the ionic transport and distribution of ions in the film. As we can see clearly in this video, the solute transport is significantly influenced and slowed down as we increase the oil surface charge density. And this is quite in agreement with what we saw in the mixing experiments. I would like to wrap up my talk with some concluding remarks. Low salinity water flooding is a mild reactive process due to a strong solid-liquid and liquid-liquid interactions. It is a multi-timescale process wherein fast in the order of milliseconds to minutes and slow in the order of hours to day sub-processes can occur simultaneously. Thin film phenomena, for example electrodiffusion, which is thought to drive wettability alteration by low salinity water, is a very slow process. To evaluate low salinity water flooding for candidates properly, particularly in the laboratory tests such as core floods, and to avoid false negatives, it is crucial to design the experiments to account for the time scale we observe in the experiments. The time scale of thin film phenomena is not scale dependent, so in the field more or less similar time scale can be expected, of course depending on the size of remaining oil ganglia and its distribution. Thank you for your attention to my presentation, and I would be happy to take your questions.
Thank you all that you are having here connected right now. We're going to do an active pause just to stress ourselves and be ready for our panel. Appreciate it. we are going to do. Okay.
Close your eyes and slightly squeeze them while pursing your lips as if you want a kiss. Pull the end of your eyes softly with your fingers. In this position, move your eyeballs left, right, right, left, repeating. Use your fingers to prevent the forehead from going upward. And now move your eyebrows upwards and hold this position. There should be no wrinkles seen on your forehead.
Okay, thank you everyone. I appreciate it. We can put on the cameras and let's be here connected ourselves with our great panelists. Thank you for being here today. An amazing presentation. Thank you, Dr. Emma Al-Salabi. Thank you, Dr. Tina Punterbo, Dr. Pedram Mazahari, Ivan Piñeres, Dr. Hassan Mahani. Thank you for great presentations as we have been getting some feedback and discussion together. So I invite to all the attendees to please open the cameras. Let's take a group photo before we start the panel. It's quite long day now. It's around 2 hours. Be connected, and we know we have connection from all the places around the world. It's great to have connection from Algeria, from Argentina, from Ecuador, France, Peru, Russia, Saudi Arabia, Turkey, Egypt, Indonesia, Iraq, Pakistan, Canada, Nigeria, United Kingdom, USA, Emirates Arabs Unit, and Venezuela. Thank you very much, all of you, to be here today. Let's take a group photo and be ready for the panelists and the question to talk between our great panelists today on this topic that make us come further into our EOR, enhanced oil recovery process we have in our reservoirs. Okay, don't be shy. Let's put the camera and be ready to do the photo. Okay, Liz, Sol, let me know when you take the group photo, so like this we can start our panel discussion.
It's okay, Cesar. Yes, please.
Thank you. Thank you all. Okay, so now we come back to our panelists. Again, thank you very much, Dr. Salabi, Dr. Tina, Pedram, Dr. Ivan, Dr. Hassan. Thank you for being here. Taking the questions on Lucas Pedroni. We want to start on that one. We have been seeing here different scenarios and understanding of water composition, salinity changes, and how we miss this option on restorations and sandstone carbonate. How the question to Lucas comes to everyone and say that how could we improve the modeling of low salinity water flooding, and how we can make these simulations results happen? This is the first question. So let's start with that one and then we continue with that. Who would like to start? Okay, Dr. Rema. Khalid, thank you.
All right, thank you so much, Cesar. It's a great pleasure being here in this webinar, and I need to thank all the audience around the world for their interest and thank the expertise here for all of them sharing their inputs Just to make it short on this, I'm coming from mostly this area, and I believe in the important role of capturing geochemical reactions for more of a what we call mechanistic or predictable kind of modeling. So basically, modeling is based mainly on lab work. So first, we need to make sure our experiments, they're well designed. And here I give credit for all of the experts who shared their intuition, including the last talk by Professor Mahani on the importance of the time scale aspect. And then we need to capture those through the simulator. At every step, whenever we can have more data, which describes the changes and in composition for the rock or the water or the oil as the experiment is happening. This will help us in better tune our model, understand those geochemical reactions, and hopefully then having a kind of a formulation which will be scalable to the field, which is our overall goal out of this modeling.
Thank you, Dr. Khalid. Res, appreciate it. Dr. Tina, what about you from your point? Thank you.
Yeah, I agree with Iman here that it's important to understand the chemical processes going on and have an understanding of the mechanisms. It's not probably very easy because everyone has a different view on what's going on, but in general, I think most of us agree that some wettability alteration is taking place, and by that we increase spontaneous inhibition, and the capillary forces are becoming more important. So I think that maybe I'm not a reservoir simulator specialist, but if we could be able to better capture the capillary forces in our simulators, and that it's more predictive or accurate, then maybe we could improve in our simulations.
Thank you, Dr. Tina. Appreciate it. Dr. Hassan Mahani, what do you think about it? Thank you.
Okay. Hello, Cesar. Hello.
Hello.
And hi, everyone. It's great to be here and to connect to all these great speakers and presenters and the audience. So I think the question is already answered by Imad and Tina quite well. So I would like just to add that if we want to properly simulate low salinity flooding, we need to first specify the scale we're trying to simulate the process at. If it is a field scale, it's a different game. If it is film scale, as I showed in my slides, it's a different game. But I guess the question was more about the larger scale or continuum scale. So in that scale, if we want to really simulate the process properly, we need to take into account all the solid-liquid interactions as well as different liquid-liquid interactions leading to different kind of mechanisms. In the current state of the simulation capability, we mainly try to simulate wettability alteration via just some magic kind of interpolation algorithms, which links wettability alteration to, let's say, a bulk change of concentration or a surface concentration of a kind of a species. But that's not it. So we are not yet there. So the process is much more complex than we believe. And the current approaches are quite deterministic in a way they treat wettability alteration. We need a more mechanistic type of approaches where we do not put any kind of deterministic kind of algorithm which already says something is going to happen. We should develop models which can tell us what's going to happen. But in the current state, we say this is going to happen, simulate it for us. And I think this is not the right approach. But okay, that gives us something at least to try to simulate it, look at different cases, different scenarios, but I think we need a more kind of concrete effort to really address that.
Thank you, Dr. Hassan. I'm really appreciated to have you here as well with other speaker panelists.
My pleasure.
Consider the time difference. Thank you very much.
My pleasure.
Yeah. Dr. Ivan Piñeres or Dr. Pedran, anything to add related to it? Thank you.
Well, yes, I have a special opinion on because we know that there is a challenge, to complete a whole value change in the smart water processes, and it is the simulation. I want to do a parallel because we're in the laboratory. We're having issues with the oil itself, because what we see from the oil fundamentals is that the oil is very complex, and there has been very little attention to that phase. And then when you go and see the simulators, they treat the oil phase as a very single, homogeneous. There is no in the commercial simulators, you don't have any option to add the chemical characteristics of the oil affinity. So then the chemical processes that are added on top of that, they're not working at all for simulations. So we need a new simulator that can capture again this complexity in the oil phase. That will be a major achievement. And then I also agree with what Matt and Tina said, that to capture all these interactions, it's very important. But we actually are facing an industry that is not understanding well this important phase, which is the oil, and we're not understanding properly, the chemistry of this oil. So it will still be a big challenge, in the following years, because simulation work has been done for more than 20 years, and we still not be able to reproduce or to have very reliable forecast in this. So we hope that with the efforts, of the researchers around the world, we can move forward. But I also think that it's very important to trust in the experiments, and there could be other options to that where we can apply like models that could probably link more statistical methods in relation to the composition. And this, if you see the development of the clay-rich project, they have done like several tests on experiments, and then the part of simulation was basically fitted to give the approval of the project. So we need to trust more in the experts. And on the way, of course, I'm not saying that simulation is a lost case, but we need to fit with the more reliable information, these new simulators will find different approaches. Right now, we're also trying to use some basic approach to simulate this type of processes, but anyway, it's still challenging because the mathematical approach, it limits us to these relative permeability curves, and there is no way of capturing the wettability alteration methods in them. So we need bright minds, probably young people who are around and present in this panel could contribute with that. But I think that it is still one of the big challenges to, let's say, close the whole value chain, and move for a faster implementation of a smart water flooding. Thank you.
Thank you, Van. And completely, it's not a lost case. It's something that, and actually we have a lot of simulators connected today, so be careful, Ivan.
Thank you.
No, it's okay. Okay, yes, it's part of how we can integrate all these reactions together. And I think the way to do it as well is collaborate on this way, to share the knowledge between us, to change the different actions and reactions that we're getting. And that's the next invitation to our great panelists related to the questions we have now, is most of the questions come together with three main words: that come related to water composition, salinity changes, floods, either sandstones and carbonate, with processes on restoration, diffusion, and how we can include heterogeneities and other scenarios. So including this water composition, salinity changes, and floods process, I appreciate if some of you can connect these words and from your experience, how we can create a new phrase or scenarios related to it. So who would like to start? Dr. Hassan? Yes.
Sorry, I missed the question. Could you repeat it, Cesar, please?
Yes, Dr. Hassan. We have in most of the questions, water composition, salinity changes, blood sandstone, and carbonate. So with these three words, how we can connect it to recreate processes related to restoration, processing diffusions, with ideas that you can put together now in the panel.
Let me think about it, because I'm not sure I fully understand the question.
But I can take.
Okay,
I can take it. Yeah.
Yeah.
So just summarizing this connection, I in the last part of my presentation, I presented what it's was called like a screening test. So these are tests for reactivity, and then we take the sandstones surface, the carbonate surfaces, and we evaluate the interactions only with the brine, and then that gives us an idea if there will be potential or not. So then from there on, we come into a validation phase with a crude oil and more close to the reservoir condition to validate it. So I think the word that summarized this is the rock reactivity.
Okay, thank you, Van. Dr. Tina.
Yes, I think that it's important to clearly differentiate between carbonate chemistry and sandstone chemistry, because otherwise we get extremely confused in literature and in our work, because these rock minerals, they react completely different in contact with the different brines, and they also react completely different in contact with different oils. And we see that so some oils, they contain acids and bases, and it's quite clear that oils with a lot of bases, with a high base number, have a larger affinity to a sandstone surface than a carbonate surface. And we also know that the oils with high acid number has a high affinity to the carbonate surface and not that high affinity to the sandstone surface. So all that is very important to take into account when you do core preparations for the laboratory studies, to also not forget about the base number of the crude oil, because that is very important.
Thank you, Dr. Tina. Appreciate it. Yes, Dr. Khalid. Emma.
All right, thank you. Well, I need just to add on this. I believe that we should have what we call a magical recipe, as you say, or what I call cocktail of ions. You need to come with this recipe of your water to make sure that you get the effect of low salinity from that particular reservoir with that particular oil is maximized. Now, to me, maybe one of the reasons that this technology did not work in some part of the world, maybe because they did not come up with this magical recipe that you need really to deep experiment and screen in order to get the maximum effect. So to me, it's more or less like a case dependent. You need to treat each reservoir by itself and then get the best recipe or formulation of water that makes it work.
Thank you. Thank you, Dr. Emma. And Dr. Emma, coming to specific questions to you and to the panelists as well, how we come together all this experimental into the field applications, oil field applications. People ask how is today this water engineering injections on field activities in Emirates Arab United.
Well, thanks for the question, Sidar. Well, we have interest in this area here in UAE as other parts of the world. And we are planning on pilots. Most of those might be starting on the beginning of next year, 2022, mostly as a start in the form of low salinity water injection or water dilution. Field operators, they get scared once we start talking about engineered water and, mixing and spiking, and they have a good reason for that, which is, the souring effect and the scale formation effects that might happen in the reservoir. So as a start, we will start with water dilution as a standalone, and then we have a couple of those hybrid, what I call EOR projects. We will start maybe with water alternating gas WAG application, where we'll have CO2 and low salinity water injected in the field. So yes, those are on the agenda.
Okay, thank you, Dr. Khalid. And I remember Tina slide that bring equation. If UK did, why Norway don't? And how we can put this one on the oil fields on Norway. Tina, any comment related to field applications on Norway at all? Thank you.
Thanks for the question. I'm sorry for giving myself an applause earlier. I was pushing the wrong button when I was trying to take my hand down. But I think that in Norway, generally, a lot of the fields have good recovery levels. So maybe it's a little bit reluctant to change something that's working very well. But there is one EOR case we could maybe point to. It's not really, it was maybe not intended to be an EOR case, but it's the seawater injection in the Ekofisk chalk field. So there they have injected seawater without removing the sulfate for many years, since the 1980s. And they produce they expect to produce about 50% or so from that field, and it's a high temperature and very fracture carbonate field. So in a sense, that is an EOR field case. So I think in UAE, they might not be so afraid of injecting at least seawater, because there's no souring effect observed in that field. So that is very positive. Yeah, I think that's it from me.
Thank you, Tina. Thank you very much. Yes, Dr. Hassan, what do you think about this implementation?
Okay, that's a great question. So what I think is the correct approach is that we should not take the laboratory results directly for field prediction. What we need to get from laboratory experiments, such as core floods, centrifuge, or any other types of scale study, is to get the rel perms and capillary pressure saturation function as a function of brine salinity or composition. So we should design the test in the lab to get this out. Otherwise, we cannot say, okay, we get 20% in the lab, so it's 20% in the field, because in the field, as you know, we have a volumetric sweep, which is much, much less than 100%. And that volumetric sweep should be used as a discounting factor to really, let's say, look at field recovery results. So we should interpret the laboratory data experiments, preferably using a numerical simulator to get the rel perms out, PC out for different rock types, and then populate the reservoir model with this data and start predicting field performance using different well designs, different scenarios whatsoever. So I think that's the that would be the correct upscaling type of approach.
Okay. Thank you all to all the panelists. And I invite you all, please, there are going to be some specific questions into the chat related to how capillary effects can come together, diffusion, PV options. So I appreciate your answering to the chat. With that, we will continue the agenda. And Tina, you did not push the wrong button. You just put this one that is an amazing button that we would like to clap all of you in the reactions that you have been sharing great knowledge here on this morning now. And thank you for being here. And hopefully we'll see you later on the panel. So this action comes to all the panelists. Thank you very much. And we will continue with our agenda. Appreciate it.
Good morning. Our next speaker is the Dr. Eduardo Manrique. He is chemist, BAs and PhD from the Universidad Central de Venezuela, with the more than 32 years of the experience in the oil and gas industry, AUR, EUR, and oil field chemistry in more than 13 countries. He is now working as Technical Authority Reservoir and EUR in ACP Ecopetrol, Colombia. Dr. Manrique has participated in more than 8 publications. Today, present importance of oil burning interaction in low salinity water. Welcome, Dr. Eduardo Manrique. Thank you for being here today.
Good morning, good afternoon, or good evening, depending on which part of the world you are located. Here is speaking Eduardo Manrique. Sadly, my camera in the laptop is not working properly, though we are gonna see each other tomorrow. Also, thanks for the opportunity to present at the IEA. I have been involved in this group for so many years, and I have learned a lot in different topics of enhanced oil recovery. And today I'm gonna summarize the R&D activities we're performing in Ecopetrol in the area of low salinity and smart water flooding. And specifically, we're gonna talk today about the importance of oil and brine interactions in low salinity water flooding. I also thanks to my co-authors, and this study is part of the PhD in petroleum engineer of Gustavo Maya and the postdoc in chemistry of Dra. Carreño. They gave me the opportunity to summarize what we have accomplished so far. The outline, we're going to briefly go to a background and motivation, introduction of scope, very briefly the protocols we are considering to understand the interactions independently and together in the oil brine rock system, some of the results, and a summary conclusions. Regarding the background and motivation, it's well known in the industry that crude oil contains salts and heavy metals. So another thing that we also know that reservoir fluids are in contact for a geological period of time in reservoirs. Then, well, we produce this oil, we treat this oil, and we perform multiple analyses. And one of those is the assays we run in the crude oils. And I'm highlighting few of them. and in red, just the information we're going to be discussing today. Salt content and the evaluation of calcium, especially calcium and magnesium in the system we are evaluating today. And why is this important? Because, well, in companies like ours, where we have the whole production chain until refinery, the first step when we transport the oil, the crude oils are going to the salting units. And this is just to remove all these salts and other contaminants to minimize corrosion and other issues like potentially contaminating the catalyst, inhibit the catalyst. These activities performed at these temperatures and they use fresh water. So I'm using this desalting unit as an analog of a low salinity and how much information you can get out of there. I recommend if you have access to this information, you can understand what I'm talking about, the amount of salt and other chemicals released by the oil before it's going to distillation and its refining process. Regarding the benefits of low salinity water flooding are well documented in carbonate and sandstone. I'm not going to go over it. Multiple mechanisms have been proposed. Given that is almost reservoir specific, we cannot reach a consensus what will operate in this or other reservoir. And the studies we're doing, we started with a challenging reservoir in 2018, which is we have run several pilots here, water flooding, ASP, gel treatments, but this reservoir is a sandstone in a depositional environment, which is marine transitional, which means that it's a sandstone, but the cement is carbonates. So we have a lot of dolomites, calcium carbonate in the cement. So in order to understand the oil interaction with the waters, we took the oil and worked with different low salinity brines, including synthetic formation brine, and validated that we form spontaneous dispersion. We increase a lot the water soluble organic compounds, and the ionic composition also increases in water test at reservoir temperature for different period of times. This was presented in the last conference, IEA conference in 2019 in Cartagena here in Colombia. Once we understood this, then we start, okay, let's see, first of all, well, how my low salinity brines interact with barrier rock. We decided to move to barrier rock to understand the interactions of the fluids in a system, in a rock system that is less reactive than the one we are evaluating. And after we did that, the most important advantage we are using here is that we were able to use capillary electrophoresis to analyze the effluents every 0.25 pore volumes injected. Here we need just 20 to 30 microliters to analyze cations and another 20 microliters to analyze anions, including low molecular weights organic acids. Once we understood the kind of the baseline, we then also run core floods, sequential core floods, and we didn't use, in this case, in this study, we already are comparing sequential core floods versus independent core floods. With that, I just summarize core flood. You know very well this system. Here is the basic oil composition data. Acid number is low, but despite this apparent low salinity, it is very reactive, and the conditions of the core flood or displacement efficiencies we use. We use a synthetic field brine, and some cases we dilute it with deionized water, and also potassium chloride, magnesium and calcium chloride salts to validate the interactions we are summarizing today. The first sequential low salinity water floods, well, we reported these studies in 2020. Field brine total salinity is around 8,000 ppm. We saturated with oil, then run water fluid with the same field brine, and then diluted with deionized water. A similar experiment, we decided, well, we saw these results, well, let's include an additional step, and we saturate with oil and test the lower salinity field brines to compare the results and see if there is any difference. Next step was to run Barrera corpus without oil and alternate field brine, low salinity, specific brine of magnesium chloride, field brine, KCl, field brine, and CaCl, and without oil, and then repeat the same system with oil, resaturating in each step with original fluids. Just to get into the results, the first experiment, just in tertiary mode, water fluiding with the field brine. We diluted 50%, saw a small increment, and no further increments were observed. The most interesting thing here is that, okay, this increment in displacement efficiency can be correlated to this increase in differential pressures in the system, and we already validated that this oil with waters, low salinity waters, can form a dispersion. So it's very reactive, this oil. Okay, in this case, the next step was, okay, let's compare that with the similar experiment. And we noticed that in every single endpoint, we change the condition of the core. So initially we started with field brine, then diluted 50%, and then diluted 93%, and the recoveries are here. However, we noticed that the endpoint's initial oil saturation was totally different in each of these steps. Knowing that Barrera is not a reactive rock, we start looking in more detail, well, how can we explain the behavior of this oil in Barrera sandstone? In this particular case, we move to the interaction first, only brine and Barrera rock as a baseline, following the protocol you are seeing here. Here you see the ionic composition of the field brine, magnesium chloride, potassium, and calcium chloride. And what we did in the effluents was, okay, let's inject field brine, and I was analyzing chloride, and the dashed line is the injected concentration, and the produced is the light blue line. So in this case, we follow the field brine. In this step, we start injecting a lower salinity magnesium chloride. We see the decrease in salinity. That's what we call the low salinity effect. And then we reach the chloride concentration of the injected magnesium chloride. Then we switch again to field brine, then KCl, we reach again the injected concentration, repeated, and the calcium chloride was slightly higher, but more or less was a condition that tell us that, okay, this porous media is not really retaining or changing much. We also compare that with every single cation. For the sake of the time, I'm just comparing here the injected and produced magnesium and calcium. In this first experiment, the same sequence, field brine, the calcium content and magnesium content are shown here, 40 ppm of magnesium, 503 ppm of calcium. Remember that this reservoir is coming from a carbonate cement, This is where calcium and magnesium is coming. Then when we switch to magnesium, the decrease in calcium is evident from this dilution of the 503, and the magnesium start to increase because it's what I'm injecting, but calcium reached 0, so there's no major indications. I'm not plotting here that differential pressures are not relevant to consider that there is a important brine rock interactions in this system. Then we reinject field brine, the same, then KCl, both calcium and magnesium reach 0 because we are not injecting neither of both cations, and repeat it for calcium chloride, and the same, magnesium reach 0. And from this, the conclusion was, okay, we can use this rock to infer what's going on with the oil and this brine system we are injecting here. So here I'm showing the experiment, the first displacement efficiency, which is the injection water flooding with the field brine. This is the composition, and I'm highlighting in yellow the elements injected. The dashed line is the injection, and the solid lines are the produced. And if we can see here, we can say that there is some level of equilibrium. Both fluids or similar fluids have been in contact for a geologic period of time. There's not much ionic exchange between field brine and oil. The only thing to highlight here is that at the end, very end of the 6 pore volumes, we start producing some potassium, which is not, was not detected in the original field brine preparation. From this, if you notice, this is a very flat solution. The ionic composition is very similar to the injected one, but then we're gonna jump with magnesium chloride. We didn't see much effects. Then we move to potassium chloride. In this case, it's very interesting how the ionic exchange between it was observed in this experiment. First, we notice the low salinity. Well, this is 8,000. Remember, the chloride, the total salinity, it is just go to very low salinity because we're injecting 1,000 ppm of KCl. And in sodium, you notice that it's going down. Calcium is also going down, getting diluted. But then in this experiment, we notice the production only for short period of time of organic acid anions, which are formate and acetate. What's interesting in this equipment, capillary electrophoresis, we can measure all these elements at the same time. And the most intriguing thing here, look at the green curve, which is calcium, and the yellow is magnesium. Why, if I'm not injecting magnesium and calcium, I'm producing both cations in the system? We already saw that urea core doesn't have calcium or magnesium in their composition to justify the increments observed here. So this is what we believe is the ionic exchange and the dissolving of the crude oil in the porous medium, as I presented in the introduction. And look at the purple line is the potassium produced, which is the cation I'm injecting until it reaches its level of close to the injection concentration. The chloride, after decreasing the salinity, stayed very stable, close to the injected concentration, around 560 ppm. So this example is very interesting in how the chemical composition, because the oil and the brine of lower salinity can impact not only smart water low salinity, but several recovery processes, specifically chemical EOR. Now we switch from potassium chloride to calcium chloride, and in this case, we notice again a very stable system. First, the ionic exchange is not that active like the previous experiment, but then of course we saw the low salinity because we're injecting in this case a higher saturation of a calcium chloride 2000 ppm. And if you notice, there is a decrease in salinity, decrease in calcium because we're injecting lower salinity, but at some point it reached the injected concentration. And we can notice that there is not much ionic exchange. What I'm saying is that probably calcium and magnesium, let's go first to calcium and magnesium, are kind of stable and in pseudo equilibrium with the oil. So there's no exchange because there's no need for transfer. Let's say the oil is already saturated with calcium and magnesium, and there's no need for exchange. In this particular example, we notice a little bit longer the production of formate and acetate. So with this, what we try to say is, look, there is an important mechanisms here that probably we are not looking with this level of detail, and in some cases, who knows if the cationic exchange reported in some publications are related to these effects and not related to rock and brine interactions. Chlorine is again very close to the injected concentrations. From the displacement efficiencies, we noticed that only with potassium chloride and calcium chloride, we observe increase in differential pressures that we attribute to the microdispersions observed in bottle tests. We are trying to see if we can define some methodologies beyond microfluidics or CT scan to understand a little bit better this mechanism. But at least from these examples, it is clear that understanding the oil brine system, we can tweak the water injection to get the most benefit of smart water or low salinity water fluid. Again, in these experiments, we also noticed the change, the changing the endpoints. Water saturation look as the same curve is resaturated every time. The initial water saturation is lower and impacting, increasing the initial oil saturation and the displacement efficiencies. We see that the field brine is even better than magnesium chloride from that standpoint, and we don't see any differential pressure effects. Then we start moving again back a little bit with KCl, and the main benefit was observed with calcium chloride. So with that, I just summarize the importance of this interaction. The sequential injection is very useful to understand ionic exchange and reactions, possible reactions with and without oil. And the benefits of capillary electrophoresis was a huge advantage for these experiments. However, to interpret displacement efficiency, probably the sequential injection mode is not a good idea, but we are at this point, we are comparing these sequential core plots with independent core plots that to validate that what we're seeing is not an accumulated effect from all the brines injected in previous stages. Finally, we demonstrate the importance of these interactions, salting in or salting out effects in low salinity waters that can help us to design better smart water. And in our consideration, these effects have been overlooked, and we require further investigation to improve our pilot design. And these results will be submitted to Fuel Journal and hopefully will be available soon in the literature. Again, thanks for the invitation and looking forward to discuss with the team tomorrow. Thank you.
Our next presenter is Dr. Geoffrey Time. He graduated from Texas A&M University in 1979 and began his career as a research geochemist at the ARCO Oil and Gas in Plano, Texas. He received his PhD in geology from the University of Wyoming in 1991 and taught at California State University on Bakersfield at the Colorado School of Mines until 2005. He returned to the University of Wyoming in 2006 at the Enhanced Oil Recovery Institute. And today he is the Chief Technology Officer at the engineering Salinity and an expert in increasing oil recovery by manipulation of water chemistry. Dr. Time will present to us low salinity water flooding. What do we need to do to move forward? The economic case. He will tell us about current terminologies and summarize the current knowledge with the major challenges to widespread development and provide detailed economic evaluation of a large-scale low salinity water flooding project. Thank you very much, Dr. Time, for being with us today, and thank you very much for your presentation.
Thank you all for being here. My name is Geoffrey Thine. I'm the Chief Technical Officer at ESAL, which is short for Engineered Salinity. You can see in back of me. I want to acknowledge my co-authors today, who have really done most of this talk. I'm just kind of presenting the information they put together. The title of our talk is Low Salinity Water Flooding. What do we need to move forward? The economic case. My co-authors are Alireza Bigdeli and Vladimir Ulanov. And this whole thing started about 2 years ago when Alireza sent me an email and we started talking about low sal and the future of low sal and why low sal isn't more popular as a enhanced oil recovery technique or an improved oil recovery technique. So the promise of low sal water flooding for the last 15 years has been this technique, whether it's EOR or IOR, that can be employed techniques. It's very desirable because of the low cost of the operations. That is, we're simply modifying the water chemistry of a water flood. There's little to no environmental impact, and we have a vast experience in the industry with water flooding. And as a kind of metric of how interesting this topic has been, there's been 360 papers in the last 4 years, including 16 review papers of the 360 papers and all the papers that came before that. So obviously it's a fascinating topic and one of great potential import for the oil industry. So what are the outcomes of low salinity water flooding? This graph over here on the right is a compilation, not a complete compilation, but a compilation of a lot of results, both from experiments and field experiences between 2004 and 2014. And what we can see here is there's a wide range of recoveries. And I counted the zeros, that is a negative result or no result. We'll talk about negative results later, but no results. I included this in this compilation. And up in the upper left-hand corner of this figure on the right, you see two histograms. And a fascinating point, one's for sandstones, one's for carbonates, the blues carbonates, the brown sandstones. We get about the same wide range of recovery. And this was all triggered, all this research was really triggered by BP in the Kuparuk Reservoir, sandstone reservoir on the North Slope. And back in 2005 was their first reported and published work. And they got 10 to 15% of the original oil in place as additional recovery. So this is a tremendous number. Average recovery worldwide is about 35% at the end of water flood. So we're talking almost half again as much potentially that you can get out of both carbonate and sandstone reservoirs. Shell in Syria, published in 2010, they got 5 to 15% OOIP. That was in another pair of sandstone fields. And then there was an EORI, that's Enhanced Oil Recovery Institute of Wyoming study, in 51 fields in another sandstone where there was no additional recovery. And so both this chart and those words speak the story of low sal. which is sometimes it works great, and that's got to be a big up, and sometimes it doesn't work at all. And that's the real problem of low salinity water flooding, is how do we get rid of the zeros and move to the 10s and 15% recoveries? So first thing is we got to know how it works. And that has been an ongoing debate, incredibly large debate. We do know that it works in sandstones and it works in carbonates. We do know it doesn't always work. And so the mechanisms are unclear, but this table over on the right-hand side kind of summarizes a lot of work. And what we see is that pretty much in the recent 4 to 5 years, people have centered on wettability alteration as the key mechanism. Surface reactions and multi-ion exchange could be seen as another form of wettability alteration, or another way to say wettability alteration. And I think we get into this very large debate, which that's fine, but at our company, what we're interested in is results. So while we can continue to debate the mechanisms and do lots of experiments and do these things, what's going to be important is to find a way to move forward functionally and make this process work economically. So where are we today? Well, we have inconsistent results. That's both capitalized, and it's important. Inconsistent results in both the laboratory and field. It's long and expensive to screen, test, and model. The industry average is 3 to 5 years and costs millions of dollars. And the project economics have been rather opaque. I mean, there's just not a good paper we can go find with actual case histories where we can compute these economics, because in the end, deploying any technique in the field is going to come down to economics. Over on the right-hand side, you see ENI's workflow for screening a field. So screening is just not executing it, just figuring out, is it going to work and what's the benefit going to be, so we can do some economics and get management to approve it. And you can see they have 8 steps here. In fact, you circle back on some of these steps. Some of these steps are quick, some of these steps are long. This is why 3 to 5 years to look at a field and decide whether it's going to be worthwhile is the industry standard. And that's not a very effective standard. So what do we need? If we're going to make low salinity water flooding work, what do we need? We need predictable results. We need fast screening and laboratory testing. And we need transparent project economics, costs and benefits. You've got to be able to go to management and tell them what the benefit's going to be and what the costs are going to be. So we really need to engineer the salinity of the water flow. That's a thing that we talk about at our company. Other people may talk about it differently, but in the end, you need to know what that target salinity is, what it's going to cost you to implement it, and what the benefit's going to be. So this is one flow. This is a flow that we use at ESAL to engineer our salinity. We do screening. You see over there on the left-hand side, we take a lot of information and empirical relationships that we've developed, use those to move on, say, yeah, there's no problem here, there's no red flags, let's move to laboratory testing. We do laboratory testing, it's fairly fast. What we're looking for is wettability alteration. So we moved beyond arguing about mechanisms and said, yeah, it's wettability alteration. Can we measure wettability in the lab quickly? Can we look at the effect over there on the right-hand side in that diagram of salinity on the x-axis and wettability on the y-axis? And what we believe is that neutral wettability is where we produce the most oil. So that's our target. And what you see here is an actual case history. The current water was what they were injecting into the reservoir. We found that the target water was a different salinity. We can move the salinity at the surface with injection and move the salinity in the reservoir, thus altering the wettability and increasing recovery. That basically is what our company is about. And I think that's basically what low salinity water flooding is about. But let's get to the good stuff. So how well does it really work? What's the real advantages? How much money can you make? So we went and found a set of case histories. This is a set of conventional fields in North America. They initiated normal water flooding, reinjection of produced water in the 1980s. And then in around 2010, a decision was made on the corporate level, we're going low cell across the whole field. No preparation, no laboratory tests, no screening, none of that. They were convinced that this was going to work, they were going to do it, and they did it. And they did it in 7 fields. They injected with low salinity water 5,000 TDS from groundwater sources, and they took all the produced saline water and re-injected it in a different interval. So this is a clean sweep kind of scenario. They saw responses within 9 to 12 months of the start of injection of low salinity water flooding. It continues till today. So now we have a 10-year history on changing the water chemistry across your whole field. And I want to emphasize there was no testing or planning. It was just, we can get this low salinity source on site. We drilled some water supply wells. We plumbed up the surface differently, and off we went. So let's look at some of the results. What we see here, I've labeled the fields, sanitized this a little bit as you might expect, A, B, C, D, E, F, G. And the green fields were the ones that showed a positive result of some level. And the red field, it's very interesting, showed damage. We actually made the production worse by using low salinity water in this one field. And we'll see in more detail how that worked. What I want you to really look at here is the primary plus secondary recovery. This is pre-low salinity, and this is projected out. If you hadn't done anything, let's take it out to the economic life of the field. What would your recoveries have been? And as you can see, there was a wide range of recoveries in these fields, and that's not atypical. This is all in the same formation. It's pretty similar oil chemistry, pretty similar water chemistry. So the expectation was that all the fields would work about the same. The first thing we see is that's not the case. The second thing we see for low salinity water flooding, projecting out the benefit to the end of the life of the field that is now apparent, what we see is the recovery in percent OOIP range from about 1.1 up to 15.8. So back to that original diagram, we've got the full range of low salinity water flood effect apparent in this set of 7 fields. In some cases, by changing to low salinity water flooding and getting a better decline curve, you extended the life of the field. That's the last column. And we can talk about that in more detail in the next couple of slides. And then in the bad case, where they damage the wettability in the field, they actually reduce the field life by almost 25 years. And that's a pretty significant finding, one we didn't really expect, to be perfectly honest. But the data is the data. So let's take a close look at the data. What you're going to see here on the left-hand side is our laboratory testing, and on the right-hand side, the actual case history in the field. So this is a case where there was a benefit. And we see there at the bottom where the water source was changed, about the middle of the diagram. And you can see a well-established decline curve on water flood in the brown line, and then it's extended out. You can see where it would have been. And then there's a sharp break, and the decline rate changed from 16% to 10%. So a real benefit. We will, by the end of the life of this field, see an extra 5 million barrels. So that's a pretty substantial increase. And over on the left-hand side, you see the laboratory testing that we do anyway. What you see here is wettability on the x-axis and residual saturation on the y-axis. This curve that you see, the shaded curve, is the standard data from starting in 1950 all the way through the present. Hundreds of data points on this plot that are covered up with the shading, showing that the best recovery, or the lowest residual saturation, is at neutral wettability. And so what we saw in this particular case is the original wettability there in the red dot is somewhat water wet. By shifting to lower salinity water, you move to more neutral wet. And on the right-hand side, you see the proof of this idea that we can measure wettability in the lab and relate that to increased recovery. In fact, we predict about this recovery. So we feel that this is a really good technique to move forward with low salinity water flooding. You've got to test your water You've got to see what the wettability shift is going to be. You've got to optimize that wettability shift and get your maximum recovery. In this case, this was not optimized for maximum recovery, but still an excellent result. But what about that bad case? So same setup here. Over on the left-hand side, we see the results of the laboratory tests. What we're basically predicting by the shift in wettability to more water wet from fairly neutral wet is a decrease in recovery. And what we see over here on the right-hand side is the decline rate changed from about 6% to almost 12%. So we left in the red shaded area all that oil behind. We essentially left 16 million barrels behind by the time that this field will be shut down and reach its economic limit. This is what I would call wettability damage. You moved the wettability the wrong way. This was a one-size-fits-all solution. So that was the major problem. You didn't do your examination and your due diligence beforehand with your laboratory testing. If they had done that, we would have said, no, 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 no. Do not go to a lower salinity water. This is not always the answer. And I think that's been one of the problems with low salinity is we've tried to find a one-size-fits-all answer, and it doesn't work that way, unfortunately. It'd be great if it would. And you can see some of the numbers. There's economic numbers associated with how much money have we lost.
Okay, I think there are some internet issues right now. Let me check. Okay. So we have Dr. Jeffrey here. Thank you, Dr. Jeffrey, for being here online too. So it looks like there is something with the video. We can replay.
Yeah, Cesar, that's fine. There was only one slide left. And so I'll just take the time to say the last slide showed that what the actual benefits were on all 7 fields. And what we projected the benefit, they made about 25 million extra barrels across all the fields. And the projected benefit, if they had optimized, was about 125 million barrels. So there's something to be said for optimization and not trying to one size fits all. And I want to thank everybody for listening to the presentation. I guess I should have gone live, lesson to myself. And thank you all for being here.
No, thank you to you, Dr. Geoffrey. Really appreciated your time as well, your sharing knowledge. Appreciate it.
And I wanted to say, it's good to see so many of you here that I know personally, have met personally, or we've corresponded. It's really neat to see all these names and people here.
Yeah, and hopefully we will meet together next year on St. Petersburg, on Russia.
Crossing my fingers, my wife would love to go to St. Petersburg.
Cool, excellent. And please welcome to everybody to let the questions to Dr. Jeffrey here into the chat, and we will continue with the next speaker. Thank you. Yes, thank you.
Can you believe the video froze? Question mark. 2 histograms. % OOIP range from about 1.1
up to 15.8. So back to that original diagram, we've got the full range of low salinity apparent in this set of 7 fields.
Oh, Lord.
In some cases, by changing to low salinity water flooding and getting a better decline curve, you extended the life of the field. That's the last column. And we can talk about that in more detail in the next couple of slides. And then in the bad case, where they damage the wettability in the field, they actually reduce the field life by almost 25 years. And that's a pretty significant finding, one we didn't really expect, to be perfectly honest. But the data is the data. So let's take a close look at the data. What you're going to see here on the left-hand side is our laboratory testing, and on the right-hand side, the actual case history in the field. So this is a case where there was a benefit, and we see there at the bottom where the water source was changed, about the middle of the diagram. And you can see a well-established decline curve on water flood in the brown line, and then it's extended out. You can see where it would have been. And then there's a sharp break, and the decline rate changed from 16% to 10%. So a real benefit. We will.
Vladimir is watching, exclamation
See an
point.
extra 5 million barrels. So that's a pretty substantial increase. And over on the left-hand side, you see the laboratory testing that we do anyway. What you see here is wettability on the x-axis and residual saturation on the y-axis. This curve that you see, the shaded curve, is the standard data from starting in 1950 all the way through the present. Hundreds of data points on this plot that are covered up with the shading, showing that the best recovery, or the lowest residual saturation, is at neutral wettability. And so what we saw in this particular case is the original wettability there in the red dot is somewhat water wet. By shifting to lower salinity water, you move to more neutral wet. And on the right-hand side, you see the proof of this idea that we can measure wettability in the lab and relate that to increased recovery. In fact, we predict about this recovery. So we feel that this is a really good technique to move forward with low salinity water flooding. You've got to test your water. You've got to see what the wettability shift is going to be. You've got to optimize that wettability shift and get your maximum recovery. In this case, this was not optimized for maximum recovery, but still an excellent result. But what about that bad case? So the same setup here. Over on the left-hand side, we see the results of the laboratory tests. What we're basically predicting by the shift in wettability to more water wet from fairly neutral wet is a decrease in recovery. And what we see over here on the right-hand side is the decline rate changed from about 6% to almost 12%. So we left in the red shaded area all that oil behind. We essentially left 16 million barrels behind by the time that this field will be shut down and reach its economic limit. This is what I would call wettability damage. You moved the wettability the wrong way. This was a one-size-fits-all solution, so that was the major problem. You didn't do your examination and your due diligence beforehand with your laboratory testing. If they had done that, we would have said, no, 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 no. Do not go to a lower salinity water. This is not always the answer. And I think that's been one of the problems with low salinity, is we've tried to find a one-size-fits-all answer, and it doesn't work that way, unfortunately. It'd be great if it would. And you can see some of the numbers. There's economic numbers associated with how much money have we lost, how much have we decreased the field value. We're going to publish all this in a paper, so there'll be plenty of time to get into details when you see it all in a paper. But I can assure you that these economic models are very well done. They're very tight, and these projections are pretty sound. So what did we learn out of all this? The diagram over on the right-hand side has 3 columns: primary and secondary, that is operating the field the way you normally would. This unoptimized low salinity water flooding, which overall did produce more barrels of oil. You can see we went from about 250 to about 275 million barrels of oil by the time these fields have reached their economic life. That's a modest improvement. The OOIP for these 7 fields was about 1.2 billion barrels. So 25 is not that exciting. And then the last column is, what could you have gotten if you tested all the fields ahead of time and optimized the wettability like we do for the maximum benefit? And you can see that that's a much better scenario where you're picking up, you know, about 125 million more barrels of oil out of the 7 fields. So what did we learn out of our study on the economics of low salinity water flooding? One thing that we didn't really touch on, but if you go back to the table, you would see it, and I'm happy to go back if we have time, is that low salinity water flood results are proportional to standard water flood results. Meaning, if you have a really good water flood, you're going to get a bunch more out of a low salinity water flood. If you don't have a very good water flood, you're going to get more, but not a huge amount. You're not going to double it or something like that. In general, this 5 to 15% bracket is where you want to be. And most of that is tuning your wettability, getting your wettability to the best possible point that is practical and economic for this field. So good low salinity water floods are profitable for the most part. I don't think, you know, again, you've got to do an economic evaluation in each case, but for the most part, that's going to be true. A bad low salinity water flood can be pretty darn costly. It's kind of a new thing to recognize that maybe you don't get a 0, maybe you actually get a negative result. That's not something that we would see in an experiment, the way the experimental protocols go. So I think that's something we've missed up to this point that we can now drag out of this field data. And it's a really important point. And the other thing we see is that really every field needs a engineered salinity water flood. So rather than just saying it's just 5,000 TDS or below 5,000 TDS, you have to actually consider how you're shifting wettability. Where do I want to get to the optimum? What are the economics? You have to engineer the salinity of your water flood. So thank you all for your time today. My co-authors and I thank you for taking the time to listen to this presentation, and I look forward to any questions you may have.
Okay, we will continue now with our next speaker.
I hope you are enjoying all these presentations as much as we do. And our next presenter is Mr. Joseph Tinchituyo. He is a professor at College of Petroleum and Natural Gas Engineering at Universidad Nacional de Ingeniería in Peru. And he's a petroleum and natural gas engineer with more than 6 years of experience in areas such as reservoir engineering and energy economics. He's currently a doctoral candidate in energetics at Universidad Nacional de Ingeniería in Peru, and he's investigating about the effect of the fines transport in low salinity water flooding process in sandstone rocks through a pore network model, which is also the topic he's going to present us today, with the title Evaluation of the Main Mechanisms of the Low Salinity Water Flooding Processes using pore network models. So thank you so much, Joseph, for the information you're going to share with us today. And to the audience, as you already know, please let all your comments and questions on the chat so they can be discussed later in the panel section. And thank you so much, everyone, for your participation.
Hello to everyone. My name is Joseph Tinchituyo. I am professor at College of Petroleum and Natural Gas at Universidad Nacional de Ingeniería from Lima, Peru. Today we're going to talk about the evaluation of the main mechanisms of low salinity water flooding processes using pore network models. The structure of the presentation is like this. First, we're going to talk about the introduction, low salinity water flooding mechanisms like fine migration, pH change, formation of microemulsion. Then we're going to talk about the pore network modeling approach. I'm going to talk about my investigation that is in progress, and finally the conclusion of this presentation. Well, let's start. Low salinity water flooding is one of the most cheapest EOR techniques in comparison, for example, with a chemical EOR technique. It was developed for Tang and Moro in 1999, and then from in the last 10 years, the number of publications, the number of articles that is available in the literature increased exponentially. When we talk about it, there are not a consensus about what is the main mechanism that explain the increase of oil recovery, and also is an affordable technique that the oil company can use nowadays because it's competitive, and also can develop and can also increase the oil recovery for any oil mature field. Well, that I said, the mechanism that explain the low salinity effects mainly, the most studied was or is the wettability alteration, like that we can see the number of publications from 2015, and also is increasing from 2019. Then is the emulsification and mineral dissolution. The other mechanism that is studied is fine migration, double layer expansion, multi-component ion exchange, saponification, salting effect, salt out effect, pH, pressure, temperature, viscosity, and salinity shock. One other approach that is in study, that are studying scientific, is what happens if we don't reduce the salinity concentration. If not, we duplicate the concentration of salinity. It is possible, and also we can obtain. It's possible to obtain the increase of oil recovery, but it will depend the condition of the reservoir. Okay, entonces today the studies are changing rapidly. If we see, the low salinity water flooding can be applied to sandstone rock or carbonate rock. In this presentation is focused in sandstone rock. We can see low salinity brine injection. The primary induced reaction is in clay hydration, mineral dissolution, multi-component ion exchange, double layer expansion, salting, osmosis, and increase of viscoelasticity. The intermediate change, then we see the improved oil recovery, is the fine migration. This fine migration is about the clay hydration, mineral dissolution, and double layer expansion. Okay? This fine migration also can alter the wettability, and the multi-component ion exchange can increase the pH and also the mineral dissolution. This pH increase can alter the wettability. This pH also reduce the interfacial tension that generate emulsification. Also, the increase of viscoelasticity reduce the snap-off. And finally, we can see the improve of oil recovery. And how is the interaction? First, the brine with rock, the brine with oil, and finally, brine, oil, and rock. Like I said, there are not confusion about which is the predominant mechanism, but the most studied is the wettability alteration that explains the increase of oil recovery. Also, other important thing, the effective salinity range. In that scene, we can see the publication about the sandstone rock, in which the mechanism was found in the literature, with the main mechanism is fine migration, then wettability, double area explosion, and others that are undefined. Also, the range, the optimal salinity for injected into the reservoir is a critical point for that be studied according the condition of the reservoir, and then will be 10% of the initial condition, 5%, 1%, and also it's gonna depend of the condition of the initial water saturation and the concentration of the salinity into the water cognate. Well, for, in the last picture, on the last figures, we can see that fine migration is one important thing that we consider into the simulation. We can see in the line blue the low salinity effects in high salinity concentration, then is injected in the second step in low salinity, that is in red. The area between the line in red, the line with the line in blue, is the increase of the recovery factor for the reducing the concentration of the salinity. Well, also in that scene, we can see the transport of fines, for example, and other. In this paper developed by you et al., we can see in low salinity, that is in red color, we can see from 0 to 2 per volume injected, the fine concentration increases from 0 to near to 1000 ppm, and also reduces when the per volume injected changes from 3 to 6. But there are not, we can see any change in high salinity processes. For that reason, in low salinity, it's important to consider that the fine migration transport like a mechanism. Also, if we can see this sequential two-phase test on Berea core with 28 millidarcy permeability, in figure 6A, in A, we can see the pressure drop during a primary and secondary drainage. This primary and secondary, the primary drainage is in green and the secondary drainage is in red. In B, we can see the pressure drop during the high salinity and low salinity. This pressure drop in low salinity is constant, that is in blue, and also in low salinity, change, that is in red, change, increase. Is one thing that in change, and also this produce, is maybe one of the reasons that produce the movement of the fines into the reservoir. In C, we can see the oil production and pressure drop during injection of brine with piecewise constant decrease in salinity as the presence of residual oils, change in the concentration of the salinity. And finally, we can see in D, the breakthrough of fine concentration during injection of brine with piecewise constant decrease in salinity in tertiary mode. This is reported in Al-Zahiri in this paper. Well, on the other hand, if we see the experimental result with a mathematical modeling, in blue we have the lab result of low salinity processes. Also, this experimental and calculated pressure drop for Poseidon core fluid without fine migration modeling, okay, that is in A, and also with fine transport modeling. In B, we can see, if we consider the fine transport model like a mechanism, we can see that the match of the lab result with transport modeling is okay. For that reason, it's necessary to incorporate into the model a fine transport like a mechanism in sandstone reservoir or sandstone rock. In the study made by thesis advisor, the Dr. Mau Romero and other investigators, they studied first injected like a high salinity, 100% of brine, and low salinity 1% of the brine, like low salinity concentration. For this change, near to 12 injected brine volume, we can see the increase of oil recovery near to 2.4 in original oil in place, 2% in original oil in place. Also, in high salinity in this area, in high salinity injection, we can see that the pH is constant, little change, but it's constant. But when we pass from high salinity to low salinity, we can see the pH change from 7.7 to 9 after about 2 per volume of 1% of brine injection in this laboratory test. For that reason, one of the mechanisms that could explain the increase of oil recovery is pH, but we need a study, we need to have more laboratory tests and also mathematical modeling. Other mechanism that is proposed by some is the formation of microemulsion as mechanism driving the low salinity effect. First, in the establishment of initial condition, water wet prior to aging, mixed water after aging, also the water saline flooding, we obtain the spontaneous clay Pickering emulsification. We can see water surrounded by clay, and also the oil is out of this. This is the reason for why the increased oil recovery, because the clay stabilization Pickering emulsion, and also is general to micro scale this micro emulsification. Well, let's talk about the pore network modeling approach. Okay, according to this paper developed by Bartet et al., near to 57% of the studies is in core or reservoir, basically doing core experimental tests on laboratory using core sandstone core outcrop for laboratory tests. They use continuum description of porous medium, two-phase Darcy equation. Only 13% of the investigation is about the pore network. Also, this is in the area in which I developing my thesis, doctoral thesis. Also, it consists length scale consistence, micro CT images, also micro models, transport of oil bank formulation. This is necessary the physical concept changes, because the representation of result of lab, we interact with mathematical modeling at pore scale. Also, other 30% of the studies is in subpore, that discrete description of porous media, discretization and description of fluids is made in that kind of study. Well, if we represent one pore with other pore, is a simple representation, is an inlet in which enter the water and displace the oil. We have the throat and second pore, but we have the pore network that is visualized in 3D, is a complex simulation, but it's possible using micro CT images. This kind of representation in all access is possible downloaded from the website of Imperial College, that is developed by the Professor Martin Bloom and his collaborators that develop and also have sandstone rock and carbonate rock for study in that scene. This pore structure, this in 3D, okay, that is in gray, also is the Berea sand that is used in this study. Before water injection, oil that is in color red is injected from left to right. Then in the same rock, the water injection is due displacing the oil. First, in the field condition is in high concentration, then in low concentration. In that thing, we measure the increase or the changes in la recovery or the oil recovery factor. Well, other important things that is developed for Martinez Mendoza methodology or workflow using the port network approach to investigate the low salinity water flooding is described in this figure 13 that contains six important stages. The first stage, the port network model, basically is the network and port sites from generic raw sample, fluid phases from experimental tests. We use experimental tests like input in that scene. The result expected is the model to describe the low salinity flooding under experimental conditions. It's important recollect the data available in the literature, the results of experimental tests. Then the fluid flow, where the expected result is the pressure in each pore and flow rate in trough. It is important because we can describe at any moment how is the behavior of the fluid flow in that pore network. Then the salinity transport, where the solution of a vective diffusive transport problem is made. Then the contact angle estimation using a linear relationship where the trough contact angle value is incorporated. With advances, also the Imperial College have more advances in that field. They measure the contact angle at any moment of the fluid flow. It's amazing that they do. Then the capillary pressure, we measure or estimate the primary drainage algorithm using angle contact, where the saturation of pressure capillarity value is obtained. And finally, the relative permeability is obtained for each phases, oil or water. This part is only for validate in wetting phase. Then when the model is validated, we incorporate the equation of fines transport into this model for evaluate the behavior of this mechanism into the low salinity water flooding process. Well, let's talk about my investigation that is in progress. Like I said, I use the Berea sand that I download from the website of Imperial College. Also, I developed my own code in Python for visualize the image, and also in the left hand we can see the input or the port input, and also the port outlet that is interconnected. First, we need to delete this port that is not connected because they cause problem when we when we start the simulation. The main characteristic of this Berea sand, these have more than 26,000 capillars, more than 12,000 pores, and also this is the distribution of this capillarity that is in red and pores that is in blue. The main effect that we are measuring is the effect of fine migration in low salinity, correlated mainly with pH change and microemulsion formation. Today we validate with the result of Martinez in wettability, and also we are working in the validation or incorporating the fine migration equation into the model. Okay. In conclusions, various mechanisms have been proposed, but there has never been a comprehensive mechanism that perfectly explains the recovery increase for all the practical cases in low salinity water flooding process. And according to the literature, in sandstone rock, the main mechanism will be wettability alteration, fine migration, pH change, and formation of microemulsion. But there are not consensus about it. Pore network modeling is an advantage method to validate laboratory results with numerical simulation. Thanks a lot.
Thank you very much. Really, really appreciate it. And thank you all for your questions to put it into the panel. For the panel discussions, we really appreciate it to have it, your questions on it. So like this, we will interact. Welcome, Dr. Frank. Don't worry about it. We understand about the issues with the connections today on these different scenarios. So don't worry about it. So with that, I would like to as well welcome you to continue our different sections and scenarios we are working today. And we would like to announce that we are working today to bring the awards related in our EUR community. We have been working together on how we can recognize our community related to what we are doing today on the different scenarios and how either with women options that we would like to put it is something that we can come. And as well, we would like to invite all of you to continue progressing in our current webinar and how today we would like as well. We are on virtual mode. Next year, we are going to be on St. Petersburg on real life conditions. So in that sense, we would like to be continue tuning with our EUR proposal. Let's continue for the next section. Appreciate it.
Our next presenter is Dr. Dandina Rao, joined Louisiana State University and is currently a distinguished professor in the Craft and Hawkins Department of Petroleum Engineering. He has been involved in rock fluids interactions and enhanced oil recovery research and field project implementation since 1983. In addition to developing the gas-assisted gravity drainage process for enhanced oil recovery, Dr. Rao has invented the hydroflame process for direct contact steam generation for heavy oil and bitumen recovery and for flue gas generation for conventional light oil recovery. The dual drop, dual crystal technique for confident reservoir wearability characterization, and the vanishing interface technique for quick and cost-effective gas-oil miscibility determination. Dr. Rao holds a BTech with distinction from India, a master's degree from the University of Saskatchewan, Canada, and a PhD from the University of Calgary, Canada. He holds several patents in the US and in other countries, in addition to publishing over 125 technical papers. Recently, in 2019, Dr. Rao was elected a senior member of the US National Academy of Inventors. Dr. Rao will present to us the role of wearability alteration in low salinity water flooding USA. Remember to leave your comments and questions on the chat. They are going to be discussed on the panel section. Thank you, Dr. Rao, for being here with us today.
Hello, everyone. I'm Dandina Rao. I'm a professor of petroleum engineering at Louisiana State University, Baton Rouge, Louisiana, in the US. My research associate and my co-author on this paper is Dr. Bikash Saikia. We would like to thank the organizers of this meeting, this symposium on EOR for IEA, for giving us this opportunity to present our research results. The talk The title of my talk is The Role of Wettability Alteration in Low Salinity Water Flooding. Low salinity water flooding has received significant attention, as you can see from the number of papers. Back in 2010, we were looking at 25, 30 papers. And in 2019, as you can see, this is over 750 papers in 2019. So there is a significant interest in this area by the industry, and that's because we can avoid extensive investments associated with conventional EOR methods. And the payback is also faster, even if the incremental oil recoveries are small. And the number of papers we discussed very clearly indicate the industry's interest in this. And the snapshot of low salinity research, there is significant progress in this area. And I've listed a few things here on sandstone reservoirs. They've observed significant improvements in oil recovery and also in carbonate reservoirs. Although they're a little more complex because of the fractured nature and unfavorable wetting, initial wetting states, and so on. And the ionic composition of the injected brine and the reservoir temperature also are shown in our work and in other studies to have an influence on the amount of oil we can get out by this process of low salinity water flooding. So wettability alteration appears to be one of the main reasons in enhancing oil recovery by low sal flooding, low salinity flooding. And also we found very interestingly, like some of the other researchers also have found this, that sulfate ion in the presence of calcium and magnesium has a significant wettability effect alteration and on oil recovery in carbonate reservoirs. And we'll show some of the results to substantiate all these statements. And increasing the temperature makes the carbonate system to shift towards more water wet state. That's also been debated in the literature, but we have some good experimental evidence to make this point in this presentation. And although all these observations have been made, the clear understanding of this still seems to be elusive. From a mechanistic point of view, we are still looking for answers. Wettability, a quick definition of wettability is needed because there are so many of them out there. It's a general definition is tendency of one fluid to spread or adhere to a solid surface in the presence of another immiscible fluid. And there's more to it than what this sentence says, and we'll talk as we go along about this. And the importance of wettability is that it influences the very fluid distribution in the reservoir, where oil is located, where is water on the pore network of the reservoir rocks. So the fluid distribution, and it also affects the effectiveness of oil recovery methods we adopt in these reservoirs. So for those two very good reasons, wettability gets a lot of important attention, truly deserving attention. In general, the water advancing contact angle, which we will define in a minute, is what really characterizes the wettability, uniform state of wettabilities. Water wet, we consider the water advancing contact angle to be in the range of 0 to 60 degrees. 60 to 120 degrees would characterize the system as intermediately wet, and anything beyond 120 would be called oil wet. And the wettability alteration really means overcoming the strong rock oil adhesion interactions. And I have a 1 minute long video to make that point. And of course, relative permeabilities. But through core floods, we can determine the ability of the porous media to conduct one fluid in the presence of two or more fluids. And that relative permeability parameter, which is so important for us in our business, also depends on wettability. So these are the points that we will discuss. The objectives of this work done by one of the master students here a few years ago, was to investigate the effect of brine salinity, brine composition, and temperature on wettability. I'll try to present all these aspects and determine also in the process optimal brine composition and optimum salinity for enhancing oil recovery, and that's through core floods. And also explore the experimental data we collected in relation to the published literature to understand the mechanisms behind such wettability alterations. Methodology-wise, we used what's called a dual drop, dual crystal technique for measuring water advancing and receding contact angles. I will present briefly what this technique is in the next 2 slides or so to describe it for you. And the recovery factor determination, of course, comes from core floods. And what we have used is Silurian dolomite in place of Yates reservoir rock. All our work in the previous years has been done with Yates reservoir, which is a prolific reservoir in West Texas. We got the rocks and fluids from that formation. Oil is the Yates crude oil, and the reservoir conditions are quite easy to handle, 700 psi and 82 degree Fahrenheit. And brine, of course, we made up the brine, synthetic brine, that matches the composition of Yates reservoir brine. And core floods, of course, we do the brine flood to determine the pore volume, absolute permeability, and the oil flood then to drive the core to initial water saturation and endpoint oil permeability measurements. And water flood is then conducted with various brine compositions and salinities. And that water floods will give us the results on recovery, endpoint, relative permeability to water, and so on to complete the story of relative permeability plotting. So the relative permeability determination is done through simulation, core flood simulators, and of course further data analysis and interpretation to decipher wettability effects from these relative permeability curves we generated with varying compositions and brine salinities. This is the dual drop, dual crystal technique. As the name sounds, dual drop, dual crystal, 2 drops on 2 crystals, and that's what we start off the experiment with, and you'll see why we do that in a little bit. And next, after aging these 2 drops on these 2 crystals overnight, we flip the lower crystal upside down, and 3 things can happen. If the oil rock adhesion here is strong enough, you will see that all the oil drop is retained on the lower crystal. If the strong adhesion is weak, some part of the drop will stick to the lower crystal and most of it will float away due to buoyancy. And if the adhesion is even weaker, all of the drop will go away. In the next step, what we do is to bring down the top crystal down onto the lower crystal, towards the lower crystal, so that we mingle these 2 drops, this and this. And in this particular case, we try to bring it to the area where there was oil drop before, that same area there. And that's so important. And you'll see that in a minute. So once we do that, mingling of the drops, then we pull the lower crystal to the sideways, they shift it from outside. And these cells are high pressure cells operated at 20,000 psi and 400 degrees Fahrenheit. Those are the limits. And I'll show you the videos where we did some high pressure, high temperature work after this slide. So these, when we pull the lower crystal to the side, the drop, in its effort to get back to the equilibrium shape, it moves in this direction. And that allows the water here, the blue is water, these are crystals, either quartz or calcite or what have you. And when the drop moves, water here or brine advances over a previously oil occupied area that I'm showing here in this part. So that meets the definition. The very definition of water advancing contact angle is that the water advances over a previously oil occupied area. Only then, when it is moving and it is in the previously oil occupied area, the water oil interface, the angle measured here meets the exact definition of water advancing contact angle. And that's where the weakness has been in the literature, that some of the measurements we made also in the early stages were not meeting those definitions. And that's why there is a lack of reproducibility in the contact angle literature, quite a bit of that actually, and that has led to some skepticism as well as some confusion about this. And we have written other papers to, as much as possible, to clarify these aspects. So if anybody is interested, please reach out to me through my email address at dnrao@lsu.edu. I'll be happy to share those papers with you. This is the high pressure optical cell that we have here at LSU. This is the one that supplies the hot air to heat the box or surrounding this cell. There's a camera system. There is a prism that deflects the part of the image to the goniometer here, and part comes right through to a recording camera, and there is a light source at the back here. And the pressures, of course, pumps and compressors are used to pressurize the system. We can go up to, in this cell is particularly designed for 20,000 psi and 400 degrees F. Here is the 1-minute video on the 3 different wettability cases. The first one is water wet case. These are the oils on quartz crystal, Beaver Hill Lake fluids on quartz crystal, and the reservoir conditions were 24 MPa and 96 C. It starts off with 2 different drops placed on 2 crystals, and then the bottom one was rotated and the drop flew away because very little adhesion force. And then we mingled the 2 drops, as you saw, and pulled it to get the contact angles. I'll show you the results of. Here are the 2 drops again for the intermediately wet case at different pressures and temperatures. As we turn the crystal sideways, and you can see the drop could have gone, but it does eventually, but still leaves some oil behind because there is some adhesion force that has developed within the same time overnight. And then we mingle the 2 drops and pull the lower crystal to the sideways to make that angle of 108 degrees or so. That's what qualifies as intermediate wettability. This is the very first case, but that was quartz in the first case. This is calcite, and you can see most of the oil drops stayed. In fact, all of it stayed, and it would rather have a cohesive failure than a movement on the lower crystal surface, and that's because the adhesion forces are so strong. So what were the angles in these 3 cases? And that's what is shown here. You see that the 4 different times we measured for the water wet case, the very first case on quartz crystal, the 50, 53, 52, 50, very highly reproducible. That's why I call it a reproducible technique. That's what this is. Whereas the conventional technique of pendant drop measurements would give you 40 degrees, somewhat misleading. In the intermediate wet case, it's a different reservoir fluid and different reservoir pressures and temperatures. And again, the 4 readings are very close to each other, 108 to 110 degree range. And the oil wet case, that was the same reservoir as this, but we, instead of quartz crystals here, we used calcite crystals. You see a world of difference here, 144 to 147 degrees. Plus or minus 2 degrees is the reproducibility of this technique. And whereas if you had measured the same oil, same crystals, same conditions, you would have gotten 25 degrees from pendant drop technique, indicating this to be a water wet case, whereas in fact it is extremely oil wet. So that is the difference between this technique and the conventional ones we had been using before. So that's why we have used this technique in this study also. Here is what we did in this study in terms of salinity variation and the water advancing contact angles at ambient conditions. Here is the AH brine composition, and these are the components in the brine, and the twice diluted, 10 times diluted, 50 times diluted, and 100 times diluted. These are the cases you will see in the results slide next. And AH reservoir brine itself, as we said, it is strongly oil wet. That was the angle, 158, and these pictures are taken from those videos of each one of these experiments. And then when we did the twice the volume of the same brine, the twice diluted, and that gives you about 150, slight reduction there, but not much, still oil wet. And 10 times dilution yielded some more reduction in the advancing contact angle, but still in the oil wet range. But then when we diluted it 50 times, the AH brine, when we diluted 50 times the original concentrations, Then it yielded an intermediate contact angle of 113 degrees. And this we'll see in the core flood results also having an impact on recovery. But when we went up to 100 times dilution, the angles showed a slight increase, but very close to the border of intermediate and weakly oil wet region. About 120 was the limit. It's about 125, just over the limit of intermediate wettability. And we also did the composition variation. And what we did was each synthetic brine composition is here, and the total dissolved solids was kept constant throughout, 10.7 grams per liter. But we varied this. There was no sodium sulfate. We wanted to try the sulfate concentration effects here, and we added some sulfate here in test 1. Test 2 did not. Test 2 was just the same original brine here. And test 1, we had 2.2. That all those sodium sulfate came from NaCl concentration. This went down, and then when we added 1.1, 4.4, double that, half this, and double that, and so on. And in the last case, test 5, we took out all the salts and only added 10.7 grams per liter of Na2SO4. And these are the test identities that you will see in the next slide here showing the results. Test 1, so 158 original reservoir brine, 154 and so on, and test 4 and test 5 again, it goes back, a similar effect that you saw in the past. Here, and you will see here the salinity variation and water advancing contact angle. The salinity variation was this, as I said, up to 100 times dilution, 50 times. And the second case was brine with 4.4 grams of sulfate ion concentration. And here we see all the results here. Reservoir condition, ambient condition in red, reservoir condition in blue, and green at high temperature, 250 F. And we see that at ambient and reservoir conditions, the results are pretty close to each other, 122, 125, and so on. But 50 times dilution, of course, showed a significant reduction in the contact angle, 157 to 112 degrees. And something similar happened with the 4.4 gram per liter sulfate brine, also very close to this initial conditions. At high temperature conditions, however, the contact angles in every case is less than the room or ambient reservoir condition or ambient condition, ambient temperatures. And that is well known in carbonate systems. We have other publications that show more results of this type for better clarity. So here are the results from core flood experiments. Several core floods we did. Again, we picked the optimum cases from the previous contact angle results. H brine with 4.5 gram per liter sulfate concentration, and 50 times diluted brine. H brine, 50 times diluted here. And the salinities were the same here. This one, of course, went down 50 times. So recovery factors, 46% to 74% to 76%. So these two seem to be 50 times dilution of H brine, seem to be very close to what a brine with 4.4 gram per liter sulfate can do in many cases. And these are the saturations and endpoint relative permeabilities. And here is the simulation results. We kept all the endpoints the same to get the relative permeabilities through the core flood simulator that we used. Here the experimental data are shown shown by points, and the calculated simulated data is in the lines here. You can see we get an excellent history match of the recovery factor as well as pressure drop. And when the matches are good, we accept the relative permeability curves as being good. And this is what we did for all the core floods. And the results are shown here in terms of recovery here. The synthetic reservoir brine itself had about 45% or so, 46%. And here is the 50 times diluted brine is the red, and the green line is for brine with sulfate brine, let's call it. And they're pretty close here, about 76% or so. And so it's quite a bit of an improvement by both these techniques of diluting the brine as well as sulfate brine. And the relative permeability curves are actually plotted here as the ratio of KRW or KRO, and that's because the shift to the right indicates a definite shift in wettability towards intermediate wet, water wet situation. And by the contact angles, we can precisely say that the shift was towards intermediate wettability. And we know we have, from our own lab and other labs, there are enough publications to indicate that oil recoveries are optimum in the intermediate wet state, better than even water wet state. So that's this kind of confirmed the same results as in the past as well. So these are the same results, salinity variation and the advancing angles shown here and the recovery factors. It's just a summary slide of all the results I've discussed so far. In terms of mechanism, we were trying to relate the pH of the brine with respect to the isoelectric point of the rock surface that we have been using in our experiments, which is dolomite. And dolomite IEP, isoelectric point, is around 8.5 pH value. And at that 8.5 pH value, there is evidence that the water film collapses and the oil contacts the rock and becomes oil wet. As you move away from it and in either direction, then the wettability shifts towards intermediate wet or less oil wet, so to speak. And that's what we see here in this case, and the literature evidence is also showing the isoelectric points of alumina here and gold here and so on. They make also a similar argument, and our results also seem to support that. Here are the conclusions from our study. The measured water advancing contact angles 158 and 157, very reproducible at reservoir conditions. Our H reservoir indicates very clearly strongly oil wet nature of this formation. Significant wettability alteration from strongly oil wet to intermediate wet was observed with 50 times diluted brine at both ambient and reservoir conditions. So brine containing 4.4 gram per liter sulfate in the presence of calcium and magnesium cations has the most significant impact on changing the wettability to bring the system from strongly oil wet to intermediate wet. That was a new finding for us. And after this study was reported in an SBE paper, there are several papers that have appeared on examining the effect of sulfate ion concentration on low-sal flooding. The effect of temperature on wettability was significant, as we showed here at 250 degrees. Because we tried that because this reservoir was, steam flooding was being considered for this formation, and that's why we tried to give them some data on that. The company was working on that reservoir at the time. Core floods conducted with 4.4 gram per liter sulfate and 50 times diluted brine both gave higher oil recoveries than undiluted H brine, as we showed. And the potential mechanism seems to be, related to the isoelectric point of the rock minerals used. And well, I thank you for your attention. And if you have any questions, I'll be more than happy to answer if you could email them to me. Thank you so much and have a nice day.
Thank you very much. Please appreciate if you can add your questions. Thank you. Thank you very much. Appreciate.
Our next presenter is Dr. Hamid Hanema. He is the chair of Petroleum and Natural Gas Engineering Department in New Mexico Tech. His educational background includes a bachelor's degree in petroleum engineering from Petroleum University of Technology, a master's degree in reservoir sciences and engineering from the French Institute of Petroleum, and a doctorate in petroleum engineering from Texas A&M University. His research in this field has revolved primarily around enhanced oil recovery, unconventional oil and gas resources, and numerical modeling. Dr. Hanima will present to us the effect of exposure time and crude oil composition on low salinity water flooding, and he will tell us about some of the factors controlling rock weathability during low salinity water injection. So thank you, Dr. Hamid Hanema, for being here with us today. And to the audience, remember to send all your comments and questions on the chat so they can be discussed later on the panel section.
Hello, I hope all of you are doing well and are safe. My name is Dr. Hamid Hanema. I'm the Associate Professor and Chair of Petroleum and Natural Gas Engineering Department in New Mexico Institute of Mining and Technology, or New Mexico Tech in short. New Mexico Tech is located in the state of New Mexico, USA, city of Socorro. And this presentation is being recorded on September 14, 2021 for IEA-EUR Technical Collaboration Program. The title of my presentation is Effect of Exposure Time and Crude Oil Composition on the Low Salinity Water Flooding. In this presentation, I would like to briefly go over the background and some of the suggested mechanism of low salinity water floodings. And also I want to share some of our recent experimental studies that we have done here in New Mexico Tech on the low salinity water flooding. This survey shows that the low salinity water injection is not new. In 1959, Martin et al. Conducted a laboratory test for heavy oil recovery by fresh water injections, and he observed increasing in oil recovery. Later on, he suggested that maybe the clay swelling or in situ emulsification are being responsible for enhanced recovery. A similar result was reported in another study by Bernard et al. In 1967, in which he conducted a laboratory test involving the displacement of mineral oil by low salinity waters. He used the 1000 ppm NaCl salinity for injected water. He observed that for the water sensitive cores, in fact those cores that has a high percentage of the clay, for those core when injecting low salinity waters, higher oil productions can be observed. And more interestingly, if you go back, the field application of low salinity water injection date back to 1970s, when the productions data shows that unintentional improved recovery from low salinity water flooding. And there are a number of field examples in the Powder River Basin in Wyoming, which was flooded with the water containing as low as 1000 ppm water salinity. And but in general, historically, little attention has been paid to the impact of the brine salinity on the water flood microscopic displacement efficiency, or the possibility of additional recovery by engineering the brine ion composition, or so on. Later on, in the 1990s, actually Professor Morrow and his co-workers at the University of Wyoming conducted pioneering laboratory studies using experimental data. They investigated the influence of the brine composition on oil recovery and found out that the injecting sufficiently low brine could potentially improve oil recovery. And since then, after their works published, this effect has been followed and investigated by many researchers who would like to find out, to identify, produce, or explain the physical and the chemical mechanisms behind the low salinity effects. And recently, this method has been tested in the pilot test in the Alaska, with Webb et al. Reporting the positive result from a single well test using the reactive tracer. The field data shows that the low salinity water injection reduced the residual oil saturation near the wellbore. That was the very important field observations that shows the potential positive impact of the low salinity. I can say that based on the literature review, we can see that most of knowledge about this effect comes from the laboratory test, where we try to see the effect of different parameters and different components on the low salinity, and then through all of these sensitivity studies results, come up with the possible solutions or come up with the possible mechanism that can explain this low salinity water injections in different, let's say, conditions, and hopefully come up with the kind of screening the technology, the screening criteria for field applications. So what we know and what we don't know, and what is important and what is not important. In these slides, I want to go through some of the factors affecting the low salinity water floodings. Clay minerals. We know that the clay particles play important roles in the low salinity water injections. According to the several studies, the injection of the low salinity water enhances oil recovery only in the cores containing the clay minerals. We have different type of the clay. The reaction of these different type of the clay to the low salinity water are different. We see a very good positive response for the rocks that has a, let's say, elite, muscovite, or the colorite clay particles, and we see a weak response for the cores that containing, let's say, kaolinite clay particles. But what we know is that the clay particles represent, right? For the sandstones cores without clay but containing dolomite crystals, also we see a positive response from the low salinity water injections. The other parameter which is important is brine. Numerous studies shows that the low salinity, there should be a low salinity thresholds in order to observe the incremental oil recovery. This number is somewhere between 1,000 to 2,000 ppm. That was different type of the cartons, but which is significantly is lower than the salinity of the formation brine itself. The next important parameter is crude oil. We know that the polar components in the crude oil are necessary. From experiments with the refined oil, keeping all the parameters constant, we did not observe any extra recovery during when we adjusting the salinity of the injection brine. Similar reports actually was presented by Morris that indicating that both acidic and the basic oils are usable for low salinity water injections. The other parameter is temperature, reservoir temperature, and we know that the low salinity water floodings is dependent on the some sort is dependent on the temperatures. When we increase the temperatures, we shows more significant actually increase in the higher recovery. The last parameter is wettability. During the low water salinity floodings, core have been suggested to become more water wet as a mixed wet clay particles are released by the low salinity water. And this is commonly accepted that a mixed wet condition usually produces the least residual oil saturation after injection of several volumes. So this is kind of acceptable among the researchers in this area that the low salinity water injections take take the core, the fabric of the, let's say, the porous media from the mixed wet or weak water wetness to a more water and strong water wet. There are also some field applications of the low salinity water injections. The successful field trials, we can name the Omar field in Syria, when 10 to 15% original oil in place is reported. BB pilot test this method in the Endicott field in the North Slope, Alaska. On 1,000 feet well spacings, they observed a very slightly moderate decrease in the water cut from 95% to 92%, and a significant residual oil saturation drop from 41% to 28%, which all in all resulted in a 10% additional oil recovery at the end. In contrast, we have some unsuccessful field trials in Russia, in Syria, and in Norway, and some of these are insignificant response to the low salinity water injections related to the complexity of the geology and sometimes presence of the very saline aquifer that can mix with the low salinity water injection and try and increase the salinity of the water. We in our laboratory, we use the core flow experiments to further investigate the effect of the heavy end components of crude oil on the low salinity effects. We use 3 different crude oils, and the brine salinity range from the 500 to well over 100,000 ppm. And mostly we wanted to see the effect of the timing on the low salinity effects and see if this process is time dependent or not. The motivation of this work came from this idea that any wettability alterations on the surface of grains require time. Similar to the core agings, when we keep the core fluid saturated core in the ovens at reservoir temperature for 10 days or let's say 2 weeks, in order to restore the original rock wettability. And now we want to see if the same time dependency is required for the low salinity effect or not. For this purpose, we use a typical core flood apparatus, and we make sure that we use the maximum size of the core available to us. For experiment, we use the 16.5 inch long and 2.5 inch diameter core. The pore volume of the core was estimated to be around 252. The core is Barrow-Sanderson's with the permeability in the range of 20 to 30 millidarcy, and the porosity was estimated to be around 19. The clay content of the core was around 77%. And the reason why we use a big size core was that the majority of the low salinity core flood experiments in the literature are performed on a small core block with the length of 3 to 6 inch. The issue with the small core block is that the capillary end effects that can disturb the fluid displacement in the porous media leads to overestimation of the low salinity effect. So we try to minimize that capillary end effect with the bigger size core. At the same time, bigger pore volumes can lead to the more accurate result. Crude oil samples were used for this set of experiments. They were designated as crude oil A, Texas light crude oil B, Kuwait medium heavy crude oil, and crude oil C, which was a synthetic oil. The synthetic crude oil is highly refined mineral oil. Thus, there is no polar component in crude oil C. 3 different brine salinity were prepared. The salinity ranges from 500 to 122,000 ppm. The initial pH was set to be 7.5, and the viscosity of the brine sample ranges from the 1.2 cp to 0.91 cp. We also measured the interfacial tensions between the crude oil and the brine samples. The observation shows that the IFD does not IFD stay constant almost for all of the 3 brine samples, and were not sensitive to brine salinity. This graph shows the oil recovery profile as a percentage of original oil in place versus pore volume injected brine for different salinities. So if you look at the let's say if you look at the crude oil A, the core that's been saturated with crude oil A, after brine injections of about 4 pore volumes, the ultimate recovery factors for all the 3 cases remain very similar to very close together. For the crude oil B, as you see here, right, the ultimate recovery for low salinity brine stay around 52.7% of original oil in place, which correspond to 7.6% original oil in place increase in recovery compared to the high salinity and also the ultra low salinity cases. So we see these things, right, response from the crude oil B to the low salinity injected brine. For the crude oil C, which is actually a mineral oil, very refined mineral oils, we do not see any response to the low salinity or change in salinity of the brine, and for all these 3 cases, the ultimate recovery will stay around the 55%. So if I want to summarize what we saw in the previous slides, is that for all these 3 crude oils, we see the different response to the low changing in salinity of the injected brine. For crude oil A and for the refined mineral oils, which crude oil C, we don't see any changes, more or less similar profile or similar ultimate recovery. But for the crude oil B, which is Kuwaitians, we see a different response to the low salinity. And the reason of this different response may be related to the chemical composition of the samples. Sample B actually contains a high percentage of heavy end components, which consequently, right, this crude oil is more reactive to the surface of the clay. In other words, it has contain more concentration of polar component, which is make it more reactive to the changing in the ion concentration of the grain particles. This result shows that the crude oil with different sort of fractions responds differently to the low salinity water floodings. Among different hydrocarbons groups, polar compounds like asphalt and resins are more reactive on the surface of the clay, and the wetting property of crude oil is mainly governed by these elements. So this graph shows the drawdown pressures as a function of the pore volume injected brine for each core fluid experiment. For the crude oil A, we see a steady increase in the pressure drops until the breakthrough, and after that we see a decline in the pressure drop. For crude oil B, the story is different. After the breakthrough, we don't see a steady decline. Instead, we see the significant fluctuations in the delta P along the core, which that's related to the pore throat blockage for this type of the crude oil we have. For 500 ppm case, as you see here, right, this delta P stand above the 2 other cases, which means that the pore throat block is more severe in this case. But however, from other side, we know that the ultimate recovery for this case is lower compared to the let's say 10,000 ppm. This is interesting observation because this suggests that the clay particle movement may be the side effect of the low salinity water floodings, but not the cause. And having the higher, for example, clay particle movement does not correspond to the positive response to the low water salinity case. And the other 2 graphs here shows the effluent pH as a function of pore volumes. For all the tests we have done on the crude oil A and crude oil B, the brine pH value was close to neutral and did not show any meaningful changes or direct correlations with the injected brine salinity. In different set of experiments, we try to investigate the effect of timing on the low salinity effect. For this purpose, we inject brine with salinity of 10,000 ppm for all 3 types of crude oil of about 4 pore volumes until the oil productions drop to 0. For all these 3 cases, drop to 0, and that means that the oil phase in the core it become immobile, so it reduces the residual oil saturations. Next, we stop the water injection, brine injections. We terminate the injections and we kept the core inside the core holder for 2 weeks. And after 2 weeks, we resumed the water injections, and we wanted to see how that's going to affect the processes. So here you see the results. For sample A, after resuming the brine injections, less than 1% original oil in place of additional oil was recovered. However, the story is a little bit different for the crude oil B. When you see here, there is a significant increase in the original oil recovery factors from 53 to almost 60.2%, which means 7% increasing of the oil recovery. This is a remarkable observation that shows the effect of the exposure time between the immobile residual crude oils and the low salinity brine. It should be noted that the core sample contained 5% kaolinite, which is well known as the oil wet clay. So we assuming the core, we believe that the core is kind of mixed oil wet and water wet, or at the best is weak water wet. So this result shows how much timing is important in the low salinity water floodings. For the field implications, I don't think that's going to change anything, because in the field, the process of displacement is very slow process compared to the labs. So more or less, all these changes will happen ultimately in the field, maybe at the back of the waterfront. But for the laboratory testing, we should be very careful to design, to give a proper timing for any changes that will take place, right, on the surface of the grains or in the core. In conclusions, we studied the effect of the pH and also the fine particle productions, and we find out that this data does not confirm that the pH or the clay particles, the attachment, play a key role in the additional oil recovery during the low salinity water injections. A 2 weeks cessations in the injection of the low salinity brine added 7.6% original oil in place to the medium heavy crude oil samples. This corresponds to additional 4.9% further reductions in the residual oil saturations. We can conclude that the low salinity mechanism seems to be a time dependence. Further investigation may be required. This is an important observation that as a new controlling factor to the low salinity water injections. Thank you, everyone. And that was the end of my presentation.
Our next presenter is Dr. Lucas Pedroni. He is a senior chemist at Petrobras Research and Development Center with 12 years of experience in EOR. He led the R&D initiatives in low salinity engineered water injection for the last 3 years and currently coordinates a foam EOR project. He also acts as a focal point for EOR technologies, working as a technical interlocutor in projects with Brazilian and international universities and Petrobras partner companies. Dr. Pedroni obtained his PhD in chemical engineering from Université Pierre of Marie Curie in France, with emphasis in enhanced oil recovery with his thesis on foam EOR. He holds a bachelor degree in chemistry and technological in chemistry and a master's degree in inorganic chemistry for work with polymer with nanocomposites. He also has experience in inorganic synthetics, physical chemistry, nanotechnology, formulation, and thermomechanical processing of polymers. Dr. Lucas will present to us challenges and key aspects to engineered water injection in the Brazilian Pre-Salt, and will tell us about how they deploy engineered water injection and face the challenges in their fields. Thank you very much, Dr. Lucas, for being with us today, and thank you very much for your presentation.
Hello, everyone. First of all, I would like to thank the organizers for inviting me for this webinar. It has been a very interesting day with great discussions and presentations. I would like to now change a little bit the focus to the challenges and key aspects that we consider when we are discussing the deployment of the engineered water injection in a very challenging scenario as the Brazilian pre-salt. Here is the outline of my presentation. I will start with giving some context about the Brazilian pre-salt fields. And then what are the challenges to implement EOR technologies, especially in an offshore scenario. Then we will try to see how the engineered water injection technology can fit on all these challenges and these constraints and boundary conditions. And finally, I will close with some conclusions in my final remarks. So here we have a map of the pre-salt province. It's placed along the southeastern coast of Brazil in an area that is almost 800 kilometers long. So we have here is reservoirs in a very challenging environment with deep and ultra deep waters, very deep reservoirs that can reach around 7 kilometers. So these reservoirs operate at very high pressures. And to get to them, we have to drill through a very thick salt layer that can be up to 2 kilometers. And this salt layer is plastic. So there are considerable challenges in drilling through that. Despite these challenges, we were able to overcome this, and now we are achieving very outstanding numbers in terms of production and development on this area. So here you have some examples of these results. The production of each well is very high. We have peak production like in Búzios. The peak production was 70,000 barrels of oil equivalent per day in a single well. And Búzios is our the largest ultra deep water reservoir and our world-class asset. And in only 3 years is already producing over 700,000 barrels and is responsible for 25% of our production. The pre-salt now responds for over 70% of Brazilian production. Okay. And because of that, this is these conditions. This is a very interesting and attractive area for development, and we can see that by the increasing presence of international players. So if you see here in the map, from 2016 to the last year, we have a huge increase in the presence of other companies operating in pre-salt. And all these challenges, all the technical development that was needed to overcome this and reach the point where we are now was recognized by the last 2 of the 4 OTC awards that our company has. A key component in overcoming the challenges in the pre-salt is our research center, SEMPES. SEMPES was always linked to our production and discovery of in deep waters. It has become the largest research and development innovation complex in Latin America. You can see the numbers here, but the most important asset that we have here is the highly skilled technical team that we have here that are very talented professionals. And we are always trying to anticipate solutions for the challenges that we have today and the challenges that we will have in the future. And we are always thinking how we can improve our operations and how can we increase the values of our assets. It's with this mindset that we were able to achieve the results that I showed in the last slide, and results like this, 60% reduction in time for drilling a well and 70% reduction in the time to construct a well in the pre-salt. These results allowed us to achieve low break-even prices and very low lifting costs for production in pre-salt. And it's with the idea that we are always trying to optimize and get more value that we get to our discussion on EOR and how this can help us on that. So if you take a look on the current distribution, okay, this data is from the Energy Outlook from 2018. But if we see the current distribution of the number of EOR projects, we see that most of the projects involve the injection of CO2, and the thermal technologies is responsible for about 1/3 of these projects. But this is not the complete picture. We need to take a look on how much each technology contributes in terms of oil. And when we consider the production of each of these technologies, we see that the thermal is responsible for more than 42% of the EOR oil produced worldwide. CO2 alone has about 20%, but it's the same share with the other gas, more or less. And the chemical EOR, despite having a lower number of projects, it also has an important share here. And if you break this down even further, we see that basically thermal means steam injection, and gas is miscible injection. All right. For offshore, we cannot consider, of course, the steam injection. Okay, the thermal is out of the picture for us. We're already using in pre-salt gas injection. It's a mixture of natural gas and CO2. And we also inject water. The difference is that we don't inject with chemicals. And if you look here, basically all the chemical injection involves some kind of polymer. Now, this is very interesting, but when we look at the number of projects that we are considering here, only a small parts of them are in offshore scenarios, because offshore is much more challenging. And when we compare this production, EOR production, to the global oil production, we see that the contribution of EOR is still very small. And the reason for that is, so implementing EOR is still quite of EOR is still very small. And the reason for that is, so implementing EOR is still quite challenging. There are many reasons for that, but if we focus on three main possible reasons, we can say that EOR projects have a timeline that is very long. So it takes time to plan, to test, to implement, and it takes a lot of time to see the incremental results. So this expanded line time makes these projects more susceptible to oil prices volatility and sudden events like the pandemic that we are living. The complexity increases when you go to the ultra deep water. We will have longer response times. We will have other constraints in the operation. We will have less tolerance in the operation of the fields, and we cannot change the equipment as easy and the facilities as easy as we can do on the onshore. So all of these will increase the uncertainties of the project. Okay. The second main reason would be that because of all these uncertainties, it's very hard to actually define how much oil we are getting from the project. So we need to understand that we have the oil that we get from the field, okay? But we are comparing with a simulation of a scenario that didn't happen. And this delta oil is
Lucas, good afternoon. Are you here connected? Yes.
Yeah, I'm connected.
Yeah, maybe we can continue your presentation from your computer if you don't mind, because it looks like there is some internet issues with the video.
No problem at all.
Appreciate it, Lucas.
Okay, let's see. Can you see my screen?
Yes, sir. Thank you, Lucas.
Okay, so I think we were here, right?
Yes, Lucas.
Well,
yes, Lucas. We can put it now in presentation mode. Appreciate it.
yes, but I'm listening the audio from the video.
No, it's okay now.
It's okay. Okay,
yeah.
All right.
Thank you.
Yeah, I have a second computer here to see if is everything okay as well.
Okay.
Yeah, there's something. Okay, every time I put on presentation mode, I start to hear.
No problem. So yeah, you want to leave it like this? You can see.
No, okay. I think I know what to do here.
Okay.
Let's see. I put on presentation mode, but you are not seeing, right?
Right. We are seeing your presentation, but on edit mode.
Okay, so it's not the ideal, but let's do like this. Okay.
Yes, sure, no problem.
Because first, I'm sharing the presentation every time I enter on presentation mode. For some reason, you don't see it.
But it's coming good now. Yes, excellent. Thank you.
Okay. Okay, let's continue like that. So I was saying that it's hard to define how much oil we actually get from a EOR project because of the uncertainties. We have to compare what we actually obtained from the project with a hypothetical base case that didn't happened. And there we depend on the level of trust and how much we are confident about our simulations and our considerations, and if the base case that we did is representative of everything that happened during the project. When we go to the offshore, we have less information, we have longer time, so the uncertainties will increase. And specifically for the pre-salt, where we have the carbonate reservoirs, we have heterogeneities, concerns about wettability. the rock and fluid interactions, because we have a high pressure, high content of CO2. We have gas in the reservoir as well. And for chemical EORs, the salinity and the hardness are very challenging. So all of this will increase the uncertainty of the project and the evaluation of how much oil we actually gain. Okay, the last point that on the why it's so hard to implement in EOR that I want to highlight is that these kind of projects, they are expensive, and we need to put a lot of investment in the beginning of the project, but the time that we have for the return of these investments is usually it happens during a very long time. And it can take a very long time to start to see some gains. And when we think about this and all the uncertainties, it's hard to make the decision to invest in EOR because of we are not sure about how much oil and money we can make with them. So it will struggle to compete with other investment opportunities like infield drilling or intelligent completion or some more seismic data and for better management of the reservoir. This kind of decision depends both on the strategy of the company, but also on the government, if there is any taxes or some kind of subsidy for these kind of operations. Without that, it's really hard to implement EOR. Actually, from those 375 projects, 80% had some kind of incentive from the government. Okay, so once we consider all these limitations and the scenario of the deep offshore, we can establish some main drivers on what we should look for to try to deploy the technologies on a pre-salt field. And the base concept here is that we need to keep the process as simple as possible, using as much as possible resources that are already available at the place. We need to have an early concept thinking to go with an FPSO production unit with the facilities that we think that will be important for the further development of the field. So we can have an operation that is robust and flexible, but we will withstand any changes in this scenario in all these uncertainties. Okay, and when we think about EOR, the four main technologies that we consider based on what we live on the pre-salt, most promising for us is WAG. It's something that it's already deployed. We are using for a long time. It's a case of success. Foam technology is a way that we are studying to optimize the WAG operation. But here we are at the customized composition of the water for increased recovery is one of the technologies that has best chances to succeed in a pre-salt reservoir. We have a lot of discussions, very rich discussions about the mechanisms or how low salinity water flooding actually work, the differences in name about the low salinity, engineered water injection, and other many names that we have in the literature. But what we know is that once we change the salinity, regardless of the initial wettability of the porous media, we might trigger some rock and fluid interactions. And these rock and fluid interactions, the final result will be an improvement in oil mobility. The consensus right now is that happens through wettability alteration, but as we saw in some presentations, there might be other mechanisms that are better explained or are more realistic or easily to comprehend to explain that. The technology is very interesting for offshore scenarios because we don't need any extra chemicals, so we don't need to worry about logistics and extra costs related to chemicals, and we don't have to have more concerns about environmental impact. The oil won't be affected by the chemicals, so the technology is completely compatible with the upstream and downstream process. The better quality of the water might enable the use of other EOR offshore, like if we want to do a polymer flood, a low salinity water allows us to use lower concentration, so the economics of the project will be much improved. And if we consider the green fields, this technology has a low implementation risk. I'll tell a little bit about that later. So I just want to show very quickly some of our results, our lab results. We're using real reservoirs and fluids from the Port-Salt. Here what we have curve that we use to evaluate the performance of low salinity. What we see is the typical delay in the breakthrough. So that means that we can achieve, we can anticipate for oil production. So in terms of the economics of the project, that's very important. And of course, we have the highest potential of increase if we do this as a secondary recovery. Tertiary recovery, we don't see much impact on our scenarios. But one thing that I want to highlight here is that we are looking only at the first pore volume inject. So this for us, it symbolizes that we might have fast results. So all those considerations about the limits or the challenge, these results are indicating that the engineered water injection is resilient to and robust against all those challenges. This is the point that changes net present value evaluation and can tip the situation in favor of this kind of project. But sometimes we are too concerned about this kind of curve. But in fact, the most critical data that we need for to evaluate the performance of this injection on field are the relative permeability curves. So these are the relative permeability curves that we got from the results on the left, because these are the data that we use on the simulate, on modeling the performance on a full field scale, okay? So a typical behavior, the relative permeability of the oil is more impacted than the water. Basically, we don't see any difference in the water, but we increased the relative permeability of the oil. So the oil is, it's easier for the oil to move through the porous media once we inject the low salinity. And when we are comparing these results with the literature to see how much is the potential to increase the recovery factor from this kind of injection, what we see is that here are our results. This is in the case of the ultimate recovery, not only the first porous volume. And what we see is that these are modest, but they are in the range of what we got from carbonate reservoirs, these last three here. These first three, they are about sandstones. So what we usually see, the results are modest. The low difference in recovery factor make it more challenging to evaluate the performance on lab, because the volumes involved will be smaller and we have more imprecision during the measurements. But it is a first step. And I need to highlight for the pre-salt, we saw that we need to work with real reservoir rocks and live fluids, live oil, and equilibrated water composition because of the high pressures and the presence of CO2. This will change the pH, the chemical equilibrium between the carbonates dissolved in the water and the rock itself. And this will change how these polar components of the oil will interact both with the ionic species in the solution and the surface of the rock. So crude oil results, they give us results that are not representative of the real conditions. So we need to be very careful when we are doing this kind of experiments. And of course, since these are real reservoir rocks, we try to select the most homogeneous plugs as possible. but they always have some heterogeneities which make more complicated to evaluate the results. So to actually estimate the potential increase in recovery factor, we need the simulations and we need the data from the lab. There are some worries here, very challenges about how to upscaling these results. But at some point, we need to get to the field to do some pilots, either single or interwell, to have data representative to see if the technology will give us more oil or not. To get to my conclusions and final remarks, so based on what we saw here, EOR is challenging to apply EOR because of the economics of the project, especially when we are considering offshore. But since the offshore reservoirs, they are bigger with larger volumes of oil, they have bigger prices. So it is a very interesting environment to try new technologies. It's important to highlight that the challenges are not only technical. We need to discuss strategies and the participation of government incentive and policies to make that decision making easier for the companies. We saw that the sooner that we deploy the EOR, at least if you think from the beginning, the EOR, we can ensure that all the resources will be at place at the right moment. And we've been discussing, especially for low salinity water injection, the best potential is if we start from the beginning. If we start to inject water in another salinity and then we change, we might have we might reduce the performance of the technology. When we are dealing with a place like pre-salt, there is no clear analogs, there is no past experience. We can use as much as possible the data and the examples that we have in the literature up to now, but they are not enough. So we need to take the risk to get real field data to make our simulations more predictive, reduce operational issues and risks. And I cannot stress enough the importance of having partners to collaborate on this journey. The key points that I want to leave you with this day is that in order to operate in such challenging conditions, we need to keep the process as simple, flexible, and robust as possible to these uncertainty times that we are living. We're only able to get to the point where we are now by an intense research, development, and innovation culture and incentive. So we need to keep this strategy if you want to ensure future production and alignment of our operations with the demands that we are seeing regarding both the climate change and the energy transition. I'd like to thank Petrobras for supporting this research. The research center's EOR lab team and the characterization and recovery technology team, and now our Petrobras colleagues working on maximizing recovery. So thank you very much for your attention.
Thank you.
Luckily, we were able to do the presentation despite the technical issues.
Thank you, Lucas. Thank you, really appreciate it. And thank you all the panelists. Yes, we make it. And that's the versatility as well from the logistics team. Appreciate all the logistics support. We have it with Zoe, Liz, Adriana, Rosa, Maria Rosa. Thank you very much for this. Lucas, on the meantime, the other panelists, come please to open your cameras and welcome to come here to the round of feedback. Lucas, there are some questions related about how pressure and temperature conditions in these deep offshore reservoirs have been simulated or be acquired on the lab conditions. And other one as well is how you can get the relative permeability curves. How did you manage to get that ones?
Okay, I'll answer the last question first. So the relative permeability curves, we have a high-level petrophysics team specializing in spatial core analysis. So we have some, actually have 2 or 3 softwares that were developed internally, and even some Python algorithms. There are Excel automated worksheets that were developed to take the core flood data, the pressure and the production data, and do all the calculations to get to the relative permeability curves. But they use the base to do this is the flowing porous media equations, and they use optimizing algorithm to try to minimize the errors in fitting the data to fitting the curve to the data points. So it's there are free solutions for that, and also I think if anyone here like to use GitHub, I'm almost sure that there are some projects that are free to use that can do this calculation for you. The other question, sorry, Cesar, I didn't got.
Okay, yes. The first one is what are the pressure and temperature conditions in these deep offshore reservoirs? Were the labs experiment run on those conditions?
The temperature conditions actually in pre-salt, they are considered, they are low compared to other reservoirs, and what we say in low salinity that we want high temperatures for carbonates to speed up the process, but those results that I showed they were obtained at 90 Celsius degrees. And many of the fields that we have, for example, 2P field is between 55 and 60 degrees. We were able to achieve increase the recovery even at low temperatures. But the high temperature specification or requirement was not something that we verified as a strong selection parameter for us, at least for now. All the results that we have doesn't point that as a cutting parameter when we are doing the screening for where we should apply low salinity or not. The pressures, we actually worked at 500 bar. And we had oil samples collected at the formation. So they didn't suffer any kind of degradation, depressurization to be recombined before using these on the tests.
Thank you, Lucas. Thank you all the panelists. Thank you, Dr. Eduardo Manrique, Dr. Jeffrey Tyne, Joseph Cintulo, Hamid Rahima, Dr. Dandina Rao, for all the amazing presentations. You can turn on your cameras. Welcome to do it. One question, Jeffrey, Eduardo, related to what you have been putting on your slide and into the chats related to the lessons learned. As Jeffrey stated, was a lot of projects on water flooding starting without taking any lab considerations and issues related to the water composition and go ahead results. And Eduardo as well stated into the chat that some projects have been doing already low salinity water flooding profiles, conditions, and considerations in the field, but we are learning about it. So an experience about it that you can share with the lessons or the results that have been getting from that one, or other lesson that cannot be repeated with another issues or projects?
Hi, Jeff. Long time no see you. Now you can see the aging effects. No, but regarding the lessons learned, surprisingly, when I arrived to Colombia, I noticed that the water quality here is really good. We're performing water flooding with 3,000 TDS. from bottom aquifers, reinjecting in other formations, and two major lessons learned. Freshwater, viscous to heavy oil, we are producing more H2S. We are having SBRs, so we need some studies related to bacteria growing because the fresh water and heavy oil. I cannot extrapolate to lighter oils where we also are injecting fresh water. And we are producing emulsions that they are not too difficult to break, to treat, but are stabilized by fines. So it seems that probably we're mobilizing some fines, it could be possible, which are stabilizing those emulsions. And on top of that, we're trying to put together lessons learned in the same field. I'm referring to H2S emulsions. We have 5 patterns pumping polymer. So we have low salinity and polymer for already 5 years. We are trying to establish the difference, and hopefully we can share that through this committee, or Cesar, you can guide us where we can discuss later those results. But this is so far what we have seen in heavy oil where we are injecting. Also I have to remind that our viscous oil are deep reservoirs. So we are talking about viscous oils, but at 90 to 120 Celsius. So it's not common to see deep viscous oils like those we are operating.
Cesar, mute. Estás en mute.
Jeffrey, thank you, Liz. Some lessons from your side. Thank you, Eduardo. You are on mute, Jeffrey.
Yeah, unmute your mic, Jeff.
Here we go. Thank you, Eduardo.
Yeah.
I think the first lesson we learned so far is don't just try this with any old water, any old low salinity water. There's the unintended side effects that we saw of wettability damage. I think Eduardo's comments about H2S, I hadn't seen that before, but that's really interesting. We have, however, not dealt with very heavy oils. We go down to about 20 API. And so 20 API and temperatures as high as 80 degrees C in the field examples we've seen. The other surprise, and I think we heard about it a little earlier this morning from the Norwegian group, is we have had cases where the salinity needed to go up. And it was not particularly, something on the order of seawater. And what we saw was the wettability shift when the salinity went down, the wettability went to more water wet, which was not the way we wanted to go. And in fact, that you had to go to a more saline water. And I think the implications of that are pretty profound in our business, because really our business, while we get paid for oil, what we mostly move is water. And we move a lot of water. And we have to dispose of water a lot of times, which is an additional cost. And so the idea in a mature basin that you could, and we've seen this, potentially take produced water from one field and inject it in a different field and see a benefit, both going up and down, is fascinating. Particularly in areas like the Permian Basin in the US, in Oklahoma, state of Oklahoma, a lot of the water disposal is causing seismic events, which are highly negative. And so the government steps in, and right now their strategy has been just don't inject as much water, which suppresses production in general for those fields, particularly unconventional fields. So I think this idea that it isn't always the salinity going down, that the composition is important, and that we could, in a mature basin, become water managers in many ways while increasing production across the basin. I think that's a thing that we need to look at in the future, to look at the economics of that. I guess the other big lesson learned is that example I showed you with the 7 fields today, they did overall get 25 million more barrels. But when you contrast that to the 1.2 billion OOIP that was the potential, that was not a very profitable overall project, because there were capital expenses, there were operational expenses. We're trying to analyze that now to get a real hard number to put in the paper. So I think that that's important to kind of realize the resistance we see to this, to low salinity water flooding or making any changes, is oil companies are primarily defensive. And all you guys who work at the oil companies know that. It's all about defensive. And Lucas just talked about that. You've got to convince management that it's going to be economic. And that means that you have to link together those lab results with a field result and look at the costs and benefits. If you can do that, we get a lot more interest when we can show the economics are favorable. That helps management, not watch that part of the budget walk away to infill drilling or something else. Instead, you can stay focused on the project long enough to actually bring the results home.
Thank you, Jeffrey. Dr. Danvin and Rao, what do you think about it, these lessons? And there are some questions related to how these interactions, weightability can be behind the recovery results you present at the mechanisms. You have it. Any experience to share, Dr. Dandina, Rao? Thank you, Jeffrey.
Yes, I appreciate the question. I appreciate the opportunity of sharing our results with you all today. And it's been a very exciting meeting and hearing all the folks. And there is so much interest in this low salinity. That's nice to see as well. The question about wettability effects, there were some questions I noticed, and I also tried to answer them online, just so it's on record. The temperature of the reservoir that we worked in, the Apes reservoir, was only 81 or 82 degrees Fahrenheit, which is actually lower than the ambient temperature outside today, right here in Louisiana. So that's why the reservoir condition, the pressure was also 700 psi, but we were using dead oils anyway. There were no light ends in that oil, so the pressure couldn't make any difference in this study, in that particular study. So the temperature being very close to ambient, so there was no difference in the ambient versus reservoir condition contact angle measurements. I think that was one of the questions. The other, sorry, I forgot your question was, the other one was about, I forgot what the other question was. But the lessons, sorry, the sulfate concentration optimization, we haven't looked at optimizing it. We did some studies, and that's why I think we zeroed in on 4.4 gram per liter concentration of sulfate ions in the sodium sulfate ions, sodium sulfate salt concentration. I'll have to go back and check our results. We haven't really done quite an optimization study as such, but we are very surprised that sulfate ion concentrations that kind of concentration did match the ideal intermediate wet oil recoveries so closely. And that was quite a surprising thing for us. And that was a lesson. And I learned a lot from all of the talks since morning. I had to miss a few of them as there is a special class today because of the classes we missed during the Hurricane Ida. 1 week of classes were canceled, so I had to teach a special class today, Saturday. So I missed several of the talks in the morning. My apologies. But there was wonderful talks, and I really admired the lessons that other people have learned from this. But for the deep, Dr. Pedroni's talk was exciting. Deep water, very challenging conditions, and he was talking about well costs being so high, obviously offshore, So we have other techniques like a single well gas assisted gravity drainage process. If they're willing to talk further, we can certainly discuss that offline as well, not necessarily the water flooding or separate wells. The well costs are very high offshore, of course, everybody knows that. So this is a single well process itself, an EOR process for using just a single well, the vertical leg as the injector, horizontal legs as the producers, and so on. So we worked on that process for deep water reservoirs as well, in addition to low sal. But I really enjoyed the other people's lessons, and we hope to learn and progress based on what we learned today.
Thank you, Dr. Rao. And that is the mission of the Technology Collaboration Program, to put together, because sometimes, as we have been seeing in the chat, what the answer we are getting is something that is going to help the other research that are going on. So, and with the pleasing of all the authors, we are going to share with you the videos and the presentations. We have it, so you will have on your mail the link to the access to this conference today. And that, so, and this go, to the Joseph Cintillo comments related to, okay, how you see our this perspective that we have today here on this scenario, Joseph.
Thank you a lot for the organizer and all the speaker. I learned a lot about this interesting topic that I guess is the best thing to investigate and continue to this. I think, for example, in our university in Peru, we are in talk with a company located in Talara Basin in the northwest of Peru to use all the information such as core, mineralogy results, PBTI results, and this important data to work in the laboratory to test and find the brine concentration to inject in the fields as a pilot project, because they started water injection as secondary recovery since 2015, and also we believe that have a great opportunity for continuing with this interesting topic. Thank you, Cesar.
No, thank you, Joseph. And Lucas, thank you for sharing related to your challenge environment you have. We have a lot of expectancy related to resolve how we can put together CO2 with EOR, with low salinity water flooding conditions, as we have been seeing as well here, different hybrid projects, as we see on the first part of the morning as well. There are some chemical, thermal conditions, as Eduardo stated as well too, that looking into forward, how we can evolve. Something related to that you can add, Lucas?
Yes. We are studying now if there is any unforeseen impact on using low salinity in conjunction of the WAG injections that we are already using. We don't see any negative impact on that, but since the rock is reactive, we have a very detailed and deep study on the geochemical aspects of these injections. When we are trying to use any other kind of EOR, like polymer or surfactant, surfactant would be more for foam formation, so the FAWAG, foam-assisted WAG injection. We need to consider the chemical stabilities, considering the non-evident pH of these rock and fluid interactions. Once we have the contact between these fluids and the reservoir, the composition changes, and the conditions where this new composition is stable is only at high pressures. So we cannot do just a workbench test, because these won't be representative of the salinity, the pH, the hardness of the water. So the high pressure needed for the tests is one of the challenges here. And then we will have the natural challenges, that is to get chemicals that are resistant to the water composition, to the conditions that we are applying. And in case of polymers especially, but also for other chemicals, the lifespan of these chemicals inside the reservoir is important, because in the pre-salt we have well distances of up to 5 kilometers. So the breakthrough time can be over 7 years. If you are planning, for example, a polymer injection where you want to increase the sweep efficiency and you want to sweep the reservoir, this polymer need to be able to viscosify the water for 5 years or 7 years or something like that. So these are the real challenges and the points that we need to pay attention, I would say. There are others, of course, but I think these are the key points.
Thank you, Lucas. And thank you all for being here today. We really appreciate the time that you have been putting today to be connected on how we can put integration. And the challenge we have is related to water composition, salinity changes, and how we can emulate from lab and how we can put in our field with economics. And we have been facing on different questions and conditions we put it. I would like to invite everyone to the panelists. You would like to please open your cameras so we can take a group photo. On the meantime, I will come with some notes related to the next activities on the International Energy Agency. We really appreciate it. If we can put your cameras on, we can take a group photo, and please let us know when we are ready, everyone. Thank you. Appreciate it. So let's take a group photo.
Thank you.
Thank you for being here all this timing. We make it. Sorry for the technology issues we get it today, but I think we handle on the good way. And to have you here is very important for us. And we continue to know that we are continue growing in our EOR community. So in that way, we would like to continue delivering this technology collaboration pathway that we would like to put together with you. So please let me know there. We have it already in place.
Thank you.
Okay, excellent. So with that, I would like to share just the final comments related to the International Energy Agency Committee. We have a challenge to continue increasing our barrels with the different technology we have in place. So it's something that we would like to continue doing, and how we are going to be continue. Next event is already, I share the link in the chat, is Australia ERTCP. This year we should supposed to be on Australia, on Sydney connected, but we are going to do it virtually. So you are welcome, more than welcome to participate on this one. And as well, this year we are going to start to generate the EOR Awards 2021. Please be tuned related to it, because we would like to recognize the regional leaders from the different areas of the world, from the Asia Pacific, Europe, Africa, North America, Latin America, a Lifetime Achievement Award in EOR, EOR Women, Institution on EOR, Government EOR, and Young Professional EOR. And be ready for the on presence on real, as Jeffrey stated. We would like to be together next year on St. Petersburg. Looking forward to have the day to be all together. So with that, we would like to say thank you all of you for being here today. Really, really appreciate your timing, and thank you for amazing journey.
Thank you. Thank you. A wonderful organization.
Thank you.
Thank you so much, all. Thank you.
Thank you.
Thank you.
Thank you, all the speakers.
Thank you very much.
Thank you.
Thank you, Julio.
Thanks very much.
Thank you.
Till we meet again. Till we meet again. Bye-bye.
Meet you in
Thank you.
Australia.
Meet in Australia. That'll be good.
Thank you, Eduardo. Thank you, Lucas.
Thank you, everybody. It was a pleasure.
See you. Thank you for your help. Bye-bye.
Thank you,
Thank
Jeffrey.
you, Ivan.
Bye.
Thank you, Ivan.
Thank you, Lucas.
Thanks. Very nice discussion. I really enjoyed this.
Thank you, Lucas. Always a pleasure. Hope to see you soon in Sundays.
I hope that too. Bye.
Voy a cerrar la sesión porque quedaron muchos comentarios. Gracias.